but you can't see my photo.
सर आपन कैमरा टे टिके तळकू करंतु सर
काला के सर
मामा
ये एक्सपोर्ट अच्छा सर गुटी एडवर्टाइज करो सर करो वीडियो
सर तो वीडियो आसुची सर सर आपन वीडियो तो देखा जाउची
I can see you all.
आपण देखि परनाते can the admin
No, I can see you. I can see you all.
Arun is able to see you. Then I think
सर सर आपन लेफ्ट हैंड साइड रे तळे देखंतु गोटे वीडियो सिंबल टा अछि
Yes.
लेफ्ट हैंड साइड तळे सेटा को क्लिक करंतु सर सेटा रे रेड स्ट्राइक ऑफ थिबो
हां
सर आसी गले सर आपन आसी गले ऑनलाइन सर ओके के कैमरा टा तळू कर दियंतु सर आटिके तळू सर आटिके हां सर बढ़िया
आपण
सर नमस्कार
नमस्कार but yes I can see you all.
आपण को ना आसुची अरुण रथ
Arun
स्टार्ट करिया
anyway he is my grandson. You are working on this, did something I don't know.
स्टार्ट करिया
प्लीज स्टार्ट
देवाशीष म्यूट कर दिए समस्त को
हां
आ गया
सर 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 समस्त को कहि दंतु काइंडली म्यूट करिया पई आउ वीडियो भी बंद करना पई ताले डाटा जो येटा अछि सेटा कम खर्च होबो सर एक्सेप्ट स्पीकर
First of all, I am welcoming all the members of OCS, my respected teachers, all esteemed invited guests, speakers, all the participants in this OCS lecture series and international conference on recent advances in chemical science on behalf of Dhenkanal College and on my own behalf. I am also expressing my heartfelt thanks to members of Orissa Chemical Society and President Orissa Chemical Society who give us the opportunity to conduct the first OCS lecture series. Now I request Professor Dr. Sajdar Samal to preside over the meeting. Before handing over the microphone to Professor Samal, I wish to give a brief introduction of him. Dr. Samal completed his master's degree in chemistry from Ravenshaw College, Cuttack in year 1975 and Doctor of Philosophy from Utkal University in year 1985. He joined as a faculty of Chemistry in Department of Higher Education, Government of Odisha after selected through OPSC and served as lecturer and reader in different government colleges. He has also worked as visiting professor in Gwangju Institute of Science and Technology and Myonggi University, South Korea. He is the editor-in-chief of Nanoscience and Nanotechnology. He has more than 100 publications and several patents to his credit. I am fortunate enough to be his student and got PhD under his guidance. Thank you very much, sir. Now I request Professor Samal to preside over the meeting. Sir. Sir, unmute current.
Okay, got it. Now you can listen to me.
Yes, sir. Yes.
नहीं आसी
Can you
ये
listen?
नो गाने करबी बोलथरे आज नवा वोटर लिस्ट
एटा ऑन शेयर कर देलो एटा को कोन कहउछंती
सर मु म्यूट कर दोची आपण आउथ अनम्यूट करबे समस्त म्यूट ऑन कर दोची आपण निज आउथ अनम्यूट कर दो आपण आउथ अनम्यूट होन सर
आपको कहले can we start now?
Yes.
Okay. Thank you Mr. convener of this meeting, Dr. Mohanty, respected Madam Principal Dr. Mishra, she is the patron of this international conference. Secretary of Orissa Chemical Society, Dr. Mahapatra, convener of this meeting, Dr. Mohanty, members of the local organizing committee, members of the academic program committee, members of the executive body of the OCS, my revered teachers, particularly Professor Prabhat Kumar Mishra, all the senior teachers, distinguished past presidents of the OCS, chairpersons of the technical sessions, keynote speaker Professor Iyer, the distinguished plenary speakers and invited speakers, the members of the panel. Among them, we have a guest panelist, Professor Delekar, all the members of the OCS and the delegates of this conference. Welcome to Orissa Chemical Society. This is a very historic moment for OCS. This is for the first time the OCS is organizing OCS Extended Lecture Series. I thank Madam Principal and the members of the Department of Chemistry, Dhenkanal Autonomous College for hosting this historic meeting. It's heartening to note that our country is undergoing a major transformation in all fronts, particularly in higher education. Many new, well-funded academic and research institutions are coming up with strong political will of government, both in the center and state. Now we see many new international standard institutes like the IITs, IGERs, NIGERs, central universities, unitary universities, NITs, and so on. Many private institutes and universities have come up, and these institutes have proven their worth time and again. In the new education policy, allocation of funds to higher education is now several times the allocation made previously. I am sure coming 2 decades will see an unprecedented growth in higher education and research. Chemistry is the mother of many allied branches, constituting what we call chemical sciences. It is well known that a career in chemistry will be satisfying and highly rewarding. It is in this critical juncture that OCS decided to broaden its presence by way of bringing the most advanced science to the doorsteps of the young students and researchers. They are the future of our nation and they need to be properly nourished. With this vision, OCS brings the experts and students together, and this will happen more often. We shall see many such OCS extended lecture series in coming months. The meetings will cover all the zones of the state. I firmly believe that this approach will be highly rewarding. For this conference on recent advances on chemical science, we have 11 speakers. I urge upon the participants to listen to all the lectures very carefully. And most importantly for the students, please grab a paper and a pencil, a notebook and a pen, and please note down when the speakers are delivering their lectures. The traditional way of the way we take down the lectures of our teachers is still valid and important. I also request the speakers to try to present their good work in an easily understandable language within the allocated time. Science is becoming complex, therefore it is important that we keep it simple to create interest and passion in the minds of the future scientists. I once again welcome you all. Please relax and enjoy quality science. Welcome aboard. Thank you. Devasis, you can take over, or I'll
Thank you,
continue.
sir, for nice welcome address. Now I request our esteemed principal and patron of this conference, Dr. Rashmi Mishra Madam, to present her address to the gathering. Madam.
We should see her. You can unshare this PowerPoint file, I think. It's not. Yes, madam. Yes, we can see you, madam.
Devas, am I audible?
Yes, yes, madam.
Devasis?
Madam, we can hear you clearly.
Okay, okay. Good morning, sir. Esteemed President, Orissa Chemical Society, Dr. Sasadhara Samal sir, Secretary Orissa Chemical Society, Dr. P. Mahapatra, esteemed speaker, Professor Parameshwar Kumar Iyer, Professor Aditya Narayan Ponda, Dr. Subhas Kumar Sahu, Dr. Rupam Sharma, Dr. Chipam Francis, Dr. Vishnu Prasad Biswal, Dr. Madhusmita Sahu, Dr. Saroj Kumar Raut, Dr. Lakshmi Narayan Nanda, Dr. Kamalakanta Nanda, Dr. Devasis Mohanty, Convener, Organizing Secretary, Dr. Dilip Kumar Naik, Sri R.K. Kuntia, Joint Secretary, Member of Organizing Committee, and esteemed participants in the 2-day-long international conference on recent advances in chemical science organized by the Department of Chemistry, Dhenkanal Autonomous College, Dhenkanal, in collaboration with Orissa Chemical Society. A very good morning and warm welcome to you all. At the very outset, I express a deep sense of gratitude to the esteemed speaker for their kind consent to address this webinar. I also thank the Department of Chemistry, and my special thanks go to the convener, Dr. Devasis Mohanty, for organizing such a difficult time when the whole world is battling the pandemic. The topic chosen for conference is very relevant in the context of COVID-19 pandemic. The tireless efforts of scientists around the world to save the life of people. Chemical sciences have immensely contributed to the good of mankind. Scientists belonging to the field of chemistry are constantly in research and making outstanding discoveries. Awards, prizes,
Devasis, make a call to madam and maybe she has to speak again. Make a telephone call.
Network issue it might be, sir.
Just make a telephone call. Yes. Madam, your voice is not audible. Say again.
I think her contact is also lost, sir.
Okay. Okay, in the meantime, let Dr. Mahapatra to deliver his speech and we shall reconnect, madam.
YouTube रे किंतु तांकर स्पीच टा कंटिन्यू करूची.
Okay. Then let it continue. Let it continue, sir.
YouTube रे
okay. Chemical sciences, okay. Chemical sciences have immensely contributed to the good of mankind. Scientists belonging to the field of chemistry are constantly doing research and making outstanding discoveries. Awards, prizes including Nobel Prize are given to them in recognition of their significant contribution considering the present COVID-19 pandemic. Chemical scientists are making constant research to defeat this pandemic which has gripped the whole world. It is a happy thing to know that effective medicines and vaccines will be available very soon. We salute these scientists, including our beloved scientists of Orissa and Orissa Chemical Society, for their immense contribution. This conference will highlight the recent advances in chemical science, and the most significant one is certainly the research to manufacture medicines for coronavirus. In this two-day conference, we are fortunate to listen to a galaxy of eminent scholars who will broaden our horizons on the advances in chemical sciences taking place in the world. Since chemistry is a fundamental part of science and it is essentially linked to human body, chemistry is a friend to mankind. All the advances in chemical sciences are directed in the good of people. We are grateful to these scientists for their philanthropic contribution. In order to know about the recent advances in chemical science, we are going for various sources of information. But this webinar provides a single source where we can listen to the distinguished speakers and the esteemed participants about the brilliant research and discoveries in this field. I once again thank the esteemed speakers for addressing in the conference. My thanks are due to the members of organizing committee for their help. It's my pleasure to say that in its quest of academic excellence, our college in the recent past had organized national and international webinars on different topics. I urge the departments to organize more such webinars. Once again, I thank Dr. Devasis Mohanty for organizing this conference, which will not only broaden the horizons of the participants, but also pave the way for further research in chemical sciences. Thank you all. Thank you all, ladies and gentlemen. Thanks. Over to Dr. Devasis Mohanty.
Thank you, madam. A nice introduction. Now, I request Secretary OCS, Dr. P. Ranjan Mahapatra, to present his report. Professor
A very good morning to one and all. Respected teachers, my grand teachers, respected President of Orissa Chemical Society, Dr. Sasadhar Samal, esteemed Principal, Dr. Rasmi Mishra, the patron of this conference, esteemed keynote speaker, Professor Iyer, distinguished professor from different parts of India and outside India, my dear students, media, press, ladies and gentlemen. On behalf of Orissa Chemical Society, I am pleased to welcome all to the first extended lecture series of Orissa Chemical Society and International Conference on Recent Advancement in Chemical Science. I would like to inform that this is the first extended lecture series of a series of extended lecture series to be conducted by Orissa Chemical Society in this year. I am really thankful and I am privileged to say that this was the idea of our esteemed President, Dr. Sasadhar Samal, who aimed to popularize chemistry to the students who are not able to attend different annual conference and regional conference of Orissa Chemical Society, particularly the peripheral college of Orissa, and it aimed at providing a key inputs to the students and the aspirant research scholars to latest development of chemical science and its allied field. Till now, Orissa Chemical Society was confined to an annual conference and 2 or 1 regional conference every year. As we are the society and we are bounded by the bylaw, so we did not get sufficient scope to explore the different problems and the new area of chemical science, particularly for the postgraduate students and the research scholars. So the purpose of this extended lecture series is to expose the students and aspirant research scholars to different field of chemical science and also to interact with the renowned scientist, research scientist and the professor who can be who may be the potential guide for the students in the near future. The main object of this extended lecture series is to reach different postgraduate centers and the peripheral college who are always not able to attend our annual conference and regional conference. Now we are planning to conduct such type of series in different parts of Orissa, and now OCS is planning to reach each and every students, but we cannot say each and every, but most of the students who are aspiring for carrying their future in research and also in chemical science. I sincerely hope that this conference will deliberate and discuss all the different facts of this exciting topic and come up with a recommendation that will lead to open a window for pursuing research in the area of chemical science. With this, I once again welcome you all to this virtual conference. Thank you. And I also like thank to the principal Dhenkanal College and convener Dr. Devasis Manti for organizing such a wonderful conference. Thank you all, and I wish this 2 day of interaction you will enjoy. Thank you.
Thank you, Ranjan. Now it's my turn. Respected Sajda Samal, President OCS, esteemed Principal Dr. Rashmi, Pattern of Conference, my friend Dr. Ranjan Mahapatra, Secretary OCS, Professor PK Iyer, keynote speaker, all past presidents of OCS, my respected teachers, all esteemed invited guests and speakers, all the participants from across the country and overseas. Once again, I am welcoming all of you to this virtual international conference on Zoom platform during this COVID-19 pandemic. I am expressing my gratitude to President OCS and other members of OCS for introducing the innovative idea of OCS lecture series. This will be immensely beneficial to the undergraduate and postgraduate students of the peripheral educational institutes. The students will be exposed to latest advance in chemical science and will be inspired to take chemistry as career. Before 5 to 6 years, undergraduate students of chemistry prefer to do MBA, MCA, BEd, even nursing instead of post-graduation chemistry. After I have taken the responsibility of head of the department, I have tried to expose them about scope in chemical science. Now the trend, more and more students are opting for post-graduation in chemistry and aiming for building career in chemical science. The graph is taking upward direction year by year. This lecture series definitely moves the graph sharper towards upward direction. Now our students are not only selected in the leading state universities, but also central universities and other institute of national repute for post-graduation in chemistry. In this year, one of our students has been selected in JNU, while 2 in Central University Hyderabad, 3 in other central universities, and 2 other Indian universities. 6 of our students has been secured rank within 100 in the recently conducted common entrance examination for state universities. Still, there is doubt in the mind of the students and their parents in the peripheral areas about career in chemical science. Hence, this type of conference definitely boosts the confidence of the students of peripheral areas to take chemistry as career. Once again, I thank President OCS and Secretary OCS for giving us opportunity to conduct the first lecture series. It is a very proud moment for Dhenkanal Autonomous College to organize such a virtual conference. More than 550 participants have been registered for the conference, not only from every corner of Odisha, but also from different parts of country, and few overseas participants from Nepal have also registered for the conference. Out of the participants, 45% are undergraduate and postgraduate students, and another 12% are research scholars. These statistics gives a positive vibe to me as an organizer and gives satisfaction that message will be reached to the targeted audience. Again, 68% of the participants are non-OCS members. Therefore, it is an opportunity for OCS to spread its aim and objective to whole country and attract many others to join OCS and expand its horizon. Before concluding, I wish to inform all of you that attendance sheet will be given in Zoom chat box during last part of each day, and a feedback form will be given after the concluding function. Those who will submit all the attendance sheet and feedback form will get e-certificate. Participant can ask their queries through chat box. After the technical session, there will be a panel discussion. Participant can directly interact with the panelist during the discussion. Hope all of you will enjoy the conference, and since the conference is a virtual, some technical problem may arise. Kindly bear with us for those unintentional interruptions. I will not take much of your time, but before concluding, I wish to thank my principal, Dr. Rashmi Mishra, for her dynamic leadership, for which we are able to organize such conferences. I am also expressing my gratitude to my colleagues Dilip Kumar Naik and Radhikant Khuntia for providing all supports, and all other colleagues for their inspiration. Thank you all. Thank you again, and enjoy the conference. I hope it will be a success. Thank you. So now the inaugural session has come to an end, and we'll move to our business part. The first technical session will start now. So I request Professor Dr. Subhashini Lenka to preside over the meeting and chair the session. Before handing over the mic to her, I want to introduce Dr. Lenka. Professor Dr. Subhashini Lenka did both her PhD and DSc in polymer chemistry from Revensa College, Cuttack in 1980 and 1984 respectively. She did her postdoctoral research work in polymer chemistry as a Japan Society Promotion of Science Fellow at Tokyo University of Agriculture and Technology, Kognai, Japan in 1989. She also did collaboration postdoctoral research in polymer chemistry at National Institute of Sericulture and Entomological Science, Tsukuba, Japan in 1997. She also collaborative research work in Texaco INC Research and Development USA in 1995. She attended and presented a paper in polymer chemistry and chaired session on advanced polymer via macromolecular engineering conference held at Vassar campus, Dutch country in USA in 1995. 36 research scholars obtained their PhD degree, and 18 research scholars obtained their MPhil degree working under her able guidance. She has published 176 research papers, 6 review articles in various national and international journals. So we are very proud to have Madam as our chairperson for first session. Now I request Professor Dr. Subhashini Lenka to take over the meeting and chair the session.
Thank you, Devashish, for your long and very bright introduction of me. Good morning to all of you, esteemed speakers of the session, past presidents of Orissa Chemical Society, all the delegates on a Zoom platform, and my dear students. On behalf of Orissa Chemical Society, I welcome all of you. At the outset, I thank Shriman Dr. Sasadhar for giving me the opportunity to be the chairperson of this technical session. This is really proud privilege for me. I also thank the president of Orissa Chemical Society for a nice arrangement in the pandemic situation. I hope all of us will be educated from the presentation of esteemed speakers. In this technical session, there are 3 speakers, and number 1 is Professor Parameswara K. Iyer, IIT Guwahati. He is the keynote speaker. His biodata is so long, if I will speak, it will take more than a day. So I am just telling his biodata in a very brief way. The interest of Professor Iyer is on polymer, organic, inorganic, bioinorganic chemistry, asymmetric catalysis, photoelectronics devices, solar cells, and sensor applications. He is associated with a number of industrial projects. He had published hundreds of research papers in many coveted journals. He guided many students for a PhD degree. And also he has guided many students of BTech and MTech in different projects. He is the author of many books, and also he has written the book chapters of many books. He has many patents to his credit. With this short biodata, I present before you Professor Iyer and I request him to present his topic. Dr. Iyer, please.
Thank you, Dr. Lenka. It's a great honor to be part of this meeting. What I will do is I'll switch off my camera and I'm going to share my slides.
Yes.
Hopefully, the connection will remain good throughout this thing.
Okay.
Are you able to see the slides?
Yes, sir.
Is it clear now?
Fantastic. Just go ahead.
So, once again, I thank Dr. Subhasini Lenka for this introduction. I also thank the organizers, Dr. Bigyan. He called me initially, and then I was receiving mails from Professor Mohapatra and other organizing members, Dr. Mohanty, Dr. Samal, Dr. Rashmi, who are there, Professor Arun Padi, whom I have been interacting for several years now, and all the members of this OCS. I think it's a wonderful job that you all are doing, and even during the pandemic, you all have not stopped working. This shows the spirit to take chemistry forward in your state, and all the the students belong to Orissa across the country and across the world. I think this is a very good initiative, and I congratulate all the organizers for this wonderful initiative. I'm sure that the students who are listening, you all should realize the efforts being put by scientists and your teachers, and you all should make use of this wonderful opportunity. So once again, I thank you all for inviting me to be part of this wonderful conference. I have been able to do this chemistry and extend my work beyond chemistry as part of a faculty in Department of Chemistry, as well as if you see my first slide, you have this Center for Nanotechnology. Okay, so this is very important. I am also associated with the Center for Nanotechnology, and this really helps my work to expand beyond chemistry. And we are also utilizing a lot of our work that we are doing into a lot of interdisciplinary or cross-disciplinary applications. Okay, this also involves students from very different background. So I will also give a brief introduction of my students, who have been the backbone of what all we do. So this is a photo taken last year. I'm not sure if this year we'll be able to go for a picnic because very few students are here. So this is a group. Of course, there are a lot of students have left, and several students have come back. And I'll be showing work of a few of them. And as I keep going ahead, I'll also be showing their photographs. So during the whole presentation, I'll be also introducing my students who have done that work. I move ahead now. So we work on interdisciplinary areas. We work on making organic and hybrid materials and looking at their applications in various kind of devices. So the main 4 kind of devices I have shown in the middle here. These are the photovoltaic or the solar cells. We also make a lot of OLED devices. We make these organic field effect transistor devices, and along with these OFET devices, we also make various sensor devices. So even with the OFET, we have the sensor devices. So it's like an interdisciplinary area that we really explore. And most of the devices we also fabricate at IIT Guwahati. So we also have fabrication facilities that are developed at IIT Guwahati. Now, moving ahead, we also work on various kind of fluorescent sensors, and I'll be spending a lot of time on this kind of materials. So these are both polymers again and small molecules, and we study elaborately their fluorescent behavior and see their interaction with various kind of analytes. This includes, in all the forms, the solid forms, the liquid forms, and also in the gaseous forms. Okay, and we also make devices and also look at the sensor properties in all the 3 states. Even we make devices that are in the solid state or even in the platform just directly the powder form. So I move ahead. So this is the journey that I can I can say briefly that we are following in the lab. We either buy these molecules and we also synthesize them. Out of them, we also make a lot of various kind of polymers. Okay, so these polymers are semiconducting in nature, or they can also be fluorescent in nature. And as I mentioned in the previous slides, we also look for various kind of applications which are in organic light emitting diodes, photovoltaics, thin film transistors, and of course various other applications. And these applications I have just listed below: the theranostics, the optoelectronic devices, the energy, and also the environmental applications. And over the last few years, we have been very fortunate to also do some technology transfers with few industries. And I was also involved with some of my collaborators to also start a startup company. And we are trying to make flexible devices. This is below. And the first one is the RR Animal Healthcare, with which we have done a lot of different work even during the COVID time. So if time permits, I'll also show you what work we have done. The next slide I have briefly touched upon that. So the first part will be, this is how I'll be going through my lecture, and if time permits, I'll cover up to the point 5 also. Okay, so I'll just introduce the concept of AIE. This is an interesting area that has come up over the last 1.5 decades. Then we have this application of conjugated polymers for latent fingerprinting. But the same materials also have application in a lot of other healthcare applications. I'll be also touching upon the point number 2, the conjugated polymers based applications. And the first point, as I mentioned, the AI based and the sensor applications, I will also go through their applications for light emitting diodes. Okay, and especially the WP LED, that is white polymer light emitting diode. So this white LED has always been a challenge, and I'll show you just one or two contributions of how this has been very useful. And along with the point 2, the point 4 also goes in a similar line. We have conjugated polymers which have applications because they're very fluorescent. You can also use them for bioimaging applications. You can have a lot of other anti-cancerous applications, and also for neurodegenerative diseases such as the Alzheimer's disease, or this is the anti-amyloid. What I've shown here is based on this the Alzheimer's disease. And last, I will just briefly touch upon our contribution, how we could help the society in a small way with our COVID-related work with my colleagues at IIT Guwahati. And I'll just summarize this later towards the end. So for the students who are sitting here, I would like to briefly give you 2 slides of introduction. Why this field is important, and I'm sure that you all would have idea about what is fluorescence. So in this slide, if you see on the top, the mechanism what I've shown here, whenever you all would have heard about a dye called fluorescein. Yes, so this fluorescein, whenever you dissolve in water, it's quite fluorescent. Okay, but what happens that as you increase the concentration, you see that the fluorescence tends to reduce. Okay, there is in terms of science, we tell there is a quenching in the fluorescence. Okay, so this is against the property of the dye. Okay, so as you increase the concentration, usually the fluorescence tends to come down. Okay, why does that happen? I'll be showing in the below. Whereas new generation of materials, that AI materials that I'm telling, what happens that initially they are not soluble in water. Okay, so as such, when the concentration is less, you don't see any fluorescence. But as the concentration increases, you see exactly the opposite effect. Okay, you start seeing the fluorescence, and it becomes very, very bright. Okay, another advantage of this class of materials which I'll be showing is that this is like a typical cartoon of this, but the structures are represented on the right side here. You can see all of them. They consist of a different number of phenyl groups, and unlike the one that is shown on the top, you have in the case of these molecules, or which are called the aggregation cost quenching. That's what I have written as ACQ. Okay, there is a small problem in these molecules, that usually there is an aromatic core that is present in this kind of dyes. And what happens is that when the concentration increases, these dyes, okay, these aromatic dyes, they tend to stack over one another by pi interaction. This is the reason that when there is extended the stacking, you see this quenching, or basically what happens, there is a relaxation of the energy, and the light that has to come out in a bright form, usually it comes out in a non-radiative pathway. Okay, that is the reason that there is no emission. Sorry. And whereas in the case of this case of AI molecules, you have this phenyl groups that are attached to this molecule, for example, or this molecule. Okay, the tetraphenyl ethylene, there is double bond here in the middle. Okay, so in this case, the phenyl groups that are attached to this, they are not this thing, they cannot stack on each other by a pi interaction, but they can be dispersed in water. Okay, and as we increase the concentration of these dyes, they also tend to come together. So there is some sort of aggregation in this case, but due to the rotation of these flexible rotors, what happens is that they relax through a radiative pathway. Hence, in this kind of systems, instead of quenching of the fluorescence, you see there is a very bright emission. And that is the reason that now this kind of molecules are finding a lot of applications in almost every area of healthcare, in sensors, even in electronic devices, wherever you have this interaction with the light. Okay, so this is a very nice example where you can see a lot of different applications. Another very nice thing about this compound is usually whenever you talk about dye or any biological applications, you have to make sure that it is soluble in water. Okay, but whereas in this case, you don't need. In this case, you can see that there are no anionic or cationic group. Okay, there are no charge groups. These are completely the hydrophobic molecules that are attached to any core. These are a very nice advantage. Okay, so you have molecules which are only soluble in organic solvents. Okay, so when you add them to water or when you increase the ratio of water, what happens is that they tend to come together. We are forcing them to aggregate. Okay, and when you force them to aggregate, that is where this phenomenon happens. Or the aggregated state, it restricts the intramolecular rotation, and it's called the RIR effect. And when it relaxes, okay, the energy has to come out through a radiative pathway. That is where you get the light. So the advantage is you don't have to spend a lot of time in introducing the ionic groups while synthesis. Okay, so that itself is a big challenge for a synthetic chemist. Okay, so you make a molecule which is very neutral, yet you can have the properties. Okay, so and when you disperse in water, what happens? They come together, they aggregate, and when they aggregate, they also form very fine or very nice shape, very nice size, and the size is usually in nano regime. Okay, so they form nanoparticles or nano sheets or a lot of different kind of this morphology. I'll be showing some slides on that. The importance of this morphology as I go ahead. So coming to the next slide, in this case, I have shown the almost the extension of that. This is an example what I told about the fluorescein. So you all can see that in this case, fluorescein, you have this aromatic core here, and this is quite bright in the dilute state. But this is what happens. They tend to stack upon each other, and what you see is they form aggregate, and there is no fluorescence. In a solid state, it shows almost like red color, but when you shine light on that, there is absolutely no emission here. Whereas in the case of this, the tetraphenyl ethylene, very simple molecule, you have double bond here, 4-phenyl group, all the 4-phenyl group, they can rotate over this plane. Okay, and as such, they're not fluorescent. Whereas in the case of when you dissolve them in water, this is what happens. They become quite bright, and even when you increase the concentration, and this is what happens in the solid state. In the absence of light, they're white color, and when you shine light on them, they're blue color. And lot of different structures, are developed based on these kind of systems. And the TP is one of the very nice example for using or generating this AI behavior. Here again, I have shown that the same thing. You have this in the case of normal molecules, normal dyes, you have this in ACQ effect, whereas initially they are very bright and they lose the fluorescence. Whereas in the case of AIE, and in this case, this is another aggregation induced enhanced emission. In these cases, you see that in AIE initially there is no fluorescence, but with time or when you increase the concentration, you see bright light. Whereas here I have introduced another term called aggregation induced enhanced emission. In this case, that initially stage you see some light, they are fluorescent. You lose the fluorescence as you increase the concentration, and you regain back. Okay, so this is another very nice the phenomenon that has come up. The fourth one in this line is the dual state emitting material. In this case, we have got some good results even with this kind of systems. Here you see that irrespective of the solvent, whether it is organic or water, you see this bright light. Okay, and towards the end, this is CIE or the crystallization induced emission. So a lot of these organic molecules, they tend to be this crystalline. So this kind of compounds, initially they're crystalline. When you grind it, when you make them powder, they lose the fluorescence. Okay, and when you get back to crystal, or when you fume it or expose it to some kind of solvent, you get back. So this is another nice area which is coming up in a big way in the field of this organic chemistry. Okay, so what I meant to show the students especially that there are various kind of these photophysical properties which you can generate by tuning or by adding some kind of functional groups or some kind of molecules within the existing core of any molecule, and generate very nice fluorescence, and also in many cases semiconducting behavior. Okay, so this is the basic principle that how you can have a simple molecule you can start the synthesis using any of the traditional synthetic these reactions, and generate desired molecules, and have a lot of different applications which are really forefront in the application area. So I move on to now our work. Okay, I have shown some molecules based on the tetraphenyl ethylene. Now we were looking at the literature, and this molecule that I've shown here is a simple naphthalimide based derivative. Looks very, very simple. Okay, the nice thing is that based on this molecule, we can do a lot of different kind of functionalization in different places. I have shown at 2 places within this molecule where we can functionalize it. But of course, you can functionalize it a lot of additional places and generate a lot of structures. Okay, so I've listed the advantages here. I'll not read through all the points in the interest of time. But we have been also able to generate a lot of applications with this kind of molecules. I'll be showing in the next few slides how these applications have really progressed, and how simple molecules that are developed by chemists like us can have interdisciplinary applications both in the field of chemical sensors, biological sensors, and also various kind of electronic devices, like I'll be showing example memory devices or LED devices. And this molecule is also very well known to be used in thin film transistors and also in solar cell applications. Okay, so those students who are interested in exploring applications other than simple chemistry, so this area of the this developing organic molecules or organic materials is really very fascinating, very interesting. And of course there are a lot of challenges that have to be overcome. But of course if you are dedicated, if you can spend some time, you can surely get very exciting results. So I move on with the application part of this, and I'm very happy to tell that this work has been done by Niranjan Meher. He is from Orissa. So his photograph is here. I'm sure many of you would recognize. Many of you also would have teachers are there who would have taught him. He is a very good inspiration and a very sincere, very hardworking student. Presently, over the last 1 year, he has moved to University of California in San Francisco as a postdoctoral fellow. And he started with chemistry, and right now he is doing postdoc with a medical doctor. Okay, so he's working in interdisciplinary area, pursuing his applications in not just simple chemistry, but also in hardcore biology or hardcore medicine. Okay, so you can see how you start with chemistry, but your application wise you can really move on to many areas. So I'll just start with this molecule, the synthesis I've shown on the left side here. So as I mentioned in the introduction slide, 2 slides before this slide, you have this naphthalimide molecule, and this is commercially available with 1 bromide molecule here. Okay, and we have what Niranjan had done is that he functionalized this with an alkyl chain, okay, of different lengths. I'm showing here only with the 6 carbon chain, and this molecule as such it is not soluble in water. Okay, and further what we have done is we have replaced this bromide with various kind of derivatives. What I've shown here, the simple phenyl group, and the phenyl group which has an aldehyde and a lot of other groups. I'll be discussing today only about the aldehyde. So what we have shown and what was there in literature, I'm just comparing these 2 things. Like in literature, it was known that unless you have this 4 phenyl group or multiple phenyl groups, and they are able to rotate, you cannot get this AI. Okay, so for getting this aggregation induced emission property, you need multiple phenyl groups. So looking at that behavior, what we thought that by introducing this phenyl group here, we may also end up getting this AI. But unfortunately, what happened, having this one phenyl group did not give any AI property. In fact, this molecule quenched in water, and we never got the fluorescence back. Okay, now this work specially focuses on the role of introducing various functional group. It's like a functional group introduced in aggregation induced emission. So it's not just based on a single molecule, but when we add this molecule to water, this forms hydrogen bonding, and by this hydrogen bonding overall there is a restriction of the RIR behavior, and that is what generates this AIE behavior. So the next this thing, I'm just very briefly going to show you how this 2 molecule behave. In the case of this molecule, only the phenyl, you can see there is a quenching of the fluorescence. Okay, initially it is bright and there is a quenching of the fluorescence. Whereas in the case of this molecule with the aldehyde group, okay, or the formal group, you can see that initially there's an enhancement in the fluorescence, and around 60-70% it is the highest. and later on, there's a quenching in the fluorescence. So this molecule, the bright fluorescence of this molecule, we have utilized for various applications in sensors. And there's a morphological analysis. I'll show you some better images later. In this case also, the one with the formyl groups, gives, it's a little bit crystalline, and you can see from this, and a very nice structure, whereas the one with the phenyl, it doesn't give any proper morphology. So I move ahead. We have also used it for application of the detection of chemical sensors, especially hydrazine. Okay, it is carcinogenic, and even very less quantities, around 10 parts per billion, is considered to be very toxic to various human organs like liver, lungs, kidneys, and other nervous system. And another major challenge is that it's highly soluble in water. Okay, so detecting hydrazine is a challenge. It has always remained a challenge, and since it has been in the market or being used very extensively in industry. Okay, so I'll be showing that in the presence of this hydrazine, what happens to our molecule. Okay, so this is a very nice example. I'll not go into the details of all the things. The first plot, okay, here you can see the molecule is very, very bright, and when you add hydrazine to this, you can see there is a very clear quenching the fluorescence. So here you can see the change in the fluorescence. The blue color is very bright blue, and then almost you don't see any fluorescence here. And this can also be seen with the naked eye. Usually, it's colorless, but when it interacts with this hydrazine, it even binds there, and you can see the yellow color very clearly visible. Okay, and it's very, very selective. The detection limit of what we got is, is the highest that is reported in literature, that is 81 parts per trillion, which is in the lowest for hydrazine. So it's a very interesting work. What we tried to show here is that even in the presence of, if you want to generate AIE, it is not just the phenyl group, but you have to introduce a functional group. So this is a functional group driven generation of an aggregation induced emission behavior, and this can be really extended to chemical sensors. And the second part is, can we make devices or portable devices? So this is a nice example. You take filter papers, you coat, you dip it in the solution of this probe, and you can see in the solid state, or we call it an condensed state, these molecules are very, very bright. Okay, this is in the presence of UV light. Now at various concentrations, the paper strips that you have, you just show it, you keep it in the mouth of this while having hydrazine vapors here. The vapors can directly be deposited here, and you can see the change in the filter paper. There is a mark, and the limit of detection even in the gaseous state is so very, very less. Okay, so even the presence of slightest vapors of hydrazine can be detected and can be seen with the under this UV very, very easily. Okay, so even in this case, though we don't claim it to be this thing, here also, so you see a very light mark. Okay, so it's a very nice simple paper strip based device where you can detect toxic chemicals like hydrazine very easily. Further, what we have done is we have also extended this application. I'll not go into this. I think somebody is using the marker. I request to please switch off this marker. The screen is
somewhere probably is writing on this touchpad.
Yeah.
Yes, some kid maybe. Devasis, please request that anybody who is using this.
Please don't write anything in the touchpad. I request everybody.
Yes.
So I move ahead.
Please.
So this is the biological application of the same probe. In this case, we have also shown that we can use it for detection of hydrazine even in various kind of cancer cell. So we have used two type of cells, the HeLa cells and the HEK 293T cells. And again, I'm very happy that this work was also done by a student from Orissa, her name is Swagatika Panda. She came to IIT Guwahati from KITS. And the good thing about this is, we can when we use this probe in the cancer cells, we don't need to wash it. Okay, so this is very selective to cancer cells, and you can see this whenever in a plate there's a cancer cell, only the cancer cells are stained blue. Okay, the outside part, it remains really colorless, and you can visualize this very, very clearly. And in the presence of hydrazine, whenever there's a presence of hydrazine, you see there is a quenching in the fluorescence. So whenever if there are a cancerous cell, it is very, very clear, and that we can detect it very clearly that hydrazine is present in the cells and how we can bind it. So thank you, Dr. Mohanty, for clearing this. So this is also seen in the other kind of this cells, HEK cells, same thing, same behavior. So it is not just applicable to one kind of cancer cell, it's applicable to multiple cells. So I move ahead with so this is a very nice example, a very nice lead for us, that by introducing certain kind of functional group, you can prevent the pi stacking of the naphthalimide core, and that is how you can generate this AI behavior, and you can also realize a lot of applications in chemical sensors or even biological sensors. Okay, so in the we have made various other derivatives of this compound. What I showed now is a simple the derivative with one aldehyde group, but we have now functionalized this. We have made more than 20 molecules of this compound, and this was very useful for the sensor that I showed. But a lot of other molecules have multiple applications. I'll not go into the details, but you can see by small change in the functional group, you can achieve color from light blue to almost greenish or greenish yellow. The entire CI spectrum you can see, you can cover, and you can see that the change in the absorption, the emission behavior. The small introduction of a functional group or variation in the functional group within the molecule, you can get a lot of different property. And here you can see within and the powder form of this compound, they also have very nice color. This is under normal light. On the right side, the figure F is under UV light. You can see very nice colors. Okay, so and we were also fortunate to get crystal structures of various molecules. This is also the morphology, as I told. When you disperse in water, you also get beautiful shapes, beautiful sizes, and this is what we optimize for various applications. So when you add it in water, these are the molecules probably are too small to be seen very clearly. People who are seeing in mobile phone, especially, I'm sure that it may be difficult to see, but yeah, if somebody wants information, I can share that with you all later. Okay, so this is the effect of various functional group. When you introduce in the molecule, you get very nice shapes and very nice size. These are all the images we have obtained from the FESCM in our institute. So very nice shape, and this is what determines their application property. This is the packing behavior. We have also got a crystal structure of around 7 molecules, and excellent information can be obtained from this kind of molecules, that where there is pi stacking, where you can completely avoid, or how they pack in when you have different functional groups. So this all help us determine various kind of application. These are the cartoons that you have shown, how they behave in the solid state. Okay, so these are very good information to realize their properties. One property that I'm showing here is we have also used it for an electronic application or memory devices, where we have the molecule has two the fluoride here. Okay, I showed an application in the chemical and biological sensor with only this formal group. In this case, we have two these fluorides, and the main reason for using this molecule is the beautiful morphology this is that it forms, and along with a simple polymer, the polyvinyl alcohol, we can make very nice films, and these are the resistive memory devices. Okay, so you can store the memory, you can rewrite, and you can get very good information using this kind of devices. So this is another application that we have extended from simple this chemical sensor, biological sensor, to a device. The next work, we have made the system even simpler. Okay, I had shown that in this molecule there was a bromide here. We introduced the phenyl group and also the bromide. Okay, but in this case, what I have shown is that we don't need that. Now when you substitute this oxygen with a long chain alkyl group, the octadecyl, okay, 18 carbon chain, and that is sufficient enough to generate this AI behavior. So why does that happen? Is that we have compared it with smaller molecules. Here I have shown the example of only a molecule with a 6 carbon chain. Okay, so simple the naphthalimide molecule, and I compared. We have introduced the 6 carbon chain and the 18 carbon chain. So you can see the length and that is the only difference that we have here. So in this case, we have used it for application of volatile organic contaminants. They call it VOC. Sometimes they call it OVCs. Okay, and there are a lot of other systems, but in this case, we have used it as a electron deficient molecule, which are very rare in literature. Okay, without going into the introduction here, I'll just show that this molecule, unlike the nanoparticles and the nanorods that are forming, in this case, this molecule forms very nice nano sheet like structure. Okay, so the reason for this is I'll be explaining here that the long chain plays a very significant role here. The 6 carbon molecule, as I told you, there is quenching the fluorescence here. Whereas in the case of the 18 carbon chain molecule, there is an enhancement in the fluorescence, and you can see when you have water up to 99% or 99.8% water, although it's a hydrophobic compound, you see this very, very nice fluorescence here, and this is what we have used for sensing of this the organic volatile contaminants. And this is an AFM height profile, and what we can see here is that the molecule, they stack up, and around the total height of this compound is around 8 to 10 nanometer, and we can see here from this also around close to 10 nanometer. Okay, so this is how they nicely stack up. And in the presence of various kinds of organic molecules, or various solvents that we use in a laboratory, like the xylene or the mesicillin, or this metaxylene, or the xylene, the mixture of xylenes, there's a big quench in the fluorescence here. Okay, so please note that this molecule, we generate this AI behavior directly from by adding it to water, and when we add it to water, they come together, they aggregate because they're hydrophobic compounds, and the organic solvents, they are exposed like the previous the work I showed, and the detection limit that we get here is also very, very low, 103 parts per billion. Okay, I'll not go into the details of this, but the mechanism part was also very important here. This is an acceptor molecule, and there is an energy transfer from the HOMO of the molecule that we want to detect, or the analytes, to the HOMO of the acceptor molecule, and that's why the mechanism that we generate is called the acceptor induced PET mechanism. Okay, again, any student who is interested, we can discuss about this. I can elaborately explain to them. I move ahead again, the same thing. So this is more explanation of this molecule, how they stack in the presence of this long alkyl chain, the 18 carbon chain. This the backbone of this compound, they don't come next to each other. Okay, so this alkyl chain they prevent. So what we have shown that in the previous work, that to generate AIA you need a functional group, whereas in this case, without even any functional group, simple alkyl chain is sufficient to prevent this pi stacking. Okay, so this is another simple example where you can have this molecule. So I've compared it with the simple molecule without any backbone, and you can see that here there is the entire molecule is completely stacked in a pi manner, and you don't see any fluorescence. Whereas in this case, in the molecule with a 6 carbon chain, there is some fluorescence that you see, but when you increase the concentration here also, you start seeing some kind of pi stacking. However, in the case of this molecule, okay, you see in a very, very bright fluorescence, there is almost no this pi interaction in this molecule. Okay, and I'll not go into the details of this. We have got here a very, very low detection limit, and what we're able to see here is a very nice example again of detection of toxic compounds at very, very low concentration. I move ahead. I make a shift to now polymers. I'm sure that there are many people here who are very interested in this, and this is a very unique application with this conjugated polymers. We have made use of a copolymer. We have used 1, 2, and 3 different units. It's a copolymer that we have used here, and the molecule that that we have here, this is what generates that aggregation induced emission behavior. Okay, now in this case, the unit number 1. Okay, the benzimidazole unit that you see here, this is what can give color. Okay, so I can get yellow, orange, whatever color I want. When I increase the ratio of this, I can get whatever color I want. Whereas this molecule and this molecule, they give only blue color. Another interesting thing in this molecule is, I told that in the case of aggregation induced emission property, you don't need an ionic group. Okay, but in this case, we have also introduced an ionic group here. Okay, so if you see here, we have this imidazolium group that is there in this compound. Now, why do we do this? Okay, we want to use it for special application of like fingerprinting. And fingerprinting, you want to develop a rapid testing system. So in this case, if we have it in water, okay, then water takes time to evaporate. Okay, so now we have to realize that property in an opposite way. For that, now we dissolve the molecule in water and we add organic solvent to that. Okay, and if you see this image, okay, this is exactly what it tells. It's initially soluble in water. When you increase the concentration of the THF, okay, so we generate this fluorescence, and almost from around 20 to 30%, you see a very bright fluorescence. Okay, so this molecule as such is soluble in water, but we can have this fluorescence as we increase the concentration in water. So very, very simple thing. We introduce this, these ionic groups here. They're soluble in water, and it starts aggregating in the presence of an organic solvent. In this case, it's THF. it can be various other solvents can also be used, but I think that THF is a solvent which is mixable with water quite easily, and you can also evaporate it and get the desired properties. So this is a very nice and unique application that we have been able to achieve with this. You all know that the detection of the fingerprint is a very big challenge in forensic science. Okay, and these days the biometric and other things have come up, and everywhere now you have this fingerprint detection and isolation. So the traditional technique, it uses super glue fuming, or we use a cyanoacrylate vapor. And in this case, what happens is that it is not very friendly, and you end up losing the fingerprint very easily. Okay, so how to preserve it and do it in a way at room temperature. Okay, so this is very important. Now I go back to the structure. Why this is very important to have this all these groups here, the ionic groups here, the alkyl chains here, and the benzene and other groups here. Okay, this is because whenever we talk about fingerprints, it mainly comprises of sweat. Okay, that is there in our hand. And what does the sweat comprise of? It comprises of very large and charged biomolecules, which includes sebum, and this includes oily mixture of various kind of wax or waxy esters. There are various kinds of triglycerides, and of course there are also a lot of this cholesterol based compounds. And in addition to that, there is also a combination of both hydrophilic and lipophilic compounds that are possible. And unless you have a structure where you have both the ionic and the neutral compound, the oily part, the interaction will not be very good. Hence, it was decided to have this kind of structure. I show the application. So this is very simple. Now you have a thumb impression on any of the surfaces, irrespective of the surface that you have. Okay, it can be an aluminum foil, or it can be a glass slide, or adhesive tape, or a coin. Okay, irrespective of the surface, whenever you have this fingerprint, you don't even realize that you have touched its surface. When you spray this polymer, okay, and you just shake off the surface, you get this very nice images. So another beautiful thing that you see here is even if when you enlarge it, you see the black marks that are there in the intermediate. Okay, so irrespective of the fingerprints that you have, okay, the intermediate part where the impression is not there, it doesn't stain that. That means you get very clear images which can be transferred or converted into digital images very easily. Okay, and the bottom image, here I have shown that you can when you zoom in, you can see very intricate part. If there are islands here, or if there is a bifurcation, or if there is a curve, or a core, or if there is a ridge ending, and if there is a pore here, sweat pores that are there, everything can be seen very clearly. Okay, even very intricate details are there. You can get information on that very clearly. Okay, and what we saw that whenever there's a crime scene, it is likely that there is sort of blood that is there in the fingerprint. Okay, so what we have shown here is that in this image, if you see, you can only see the blood. Okay, without fluorescence. Now, whenever you shine the fluorescent light, or you can see this image is very nicely. You don't see any interaction with the blood. Okay, and when we had sent this paper, the reviewer also told that one of the reviewer told us to also try to see an abrasion test, so to scratch it and everything. So we have seen that also somebody tries to remove it any surface. So if a surface that is scratched already, even on that, if you spray, we can still get this image almost very clearly. So irrespective of the surface and irrespective of the type of material, you can get these images very clearly. This is on the glass, this is on a tin cover. You can see that you can get these images in the presence of this conjugated polymer very clearly. Okay, so this condensed state or the solid state properties of these molecules is very important to generate this the fluorescence behavior, which is very clearly visualized using this polymers. And as I mentioned, we can tune the color, change the color for whatever applications we need. Okay, I move on to another. Oh, sorry. Before I move on, we also had an invitation for writing a review article, and December issue. One of the December issues, we have shown the application of this AI-based materials in a lot of different applications, and you can see that we can identify the blood groups. You can also determine the presence of drugs, or in security log, we can identify the male or the female from the fingerprint. In biometric applications, this latent fingerprinting I already showed, and also it is used these days in almost all the airports. So the applications of this kind of polymers are not limited to just one application, but of course you have a lot of different applications that are coming up with this kind of materials. So I move on from traditional this application to device-based applications, and to generate this white light. Okay, one of the challenges that remains is that can you make a material that can have a single material that can get this white light. Okay, and usually whenever you talk about this white light, they have the CI coordinates should be close to the 0.33 and 0.33. Okay, so this is very, very important. So unless you have a material, you don't get this. Okay, there is slight variation. You may either end up in blue, green, or red, or this orange region. Okay, so traditional method is using this three colors: the blue, the green, or the red, the combination of three. Okay, I will not show today. We have already done previously about this combination of blue and orange. Okay, but in this work, what we have done is that we have now utilized only the white emitting a single material for the white light. So I'll move quickly. I'm showing up about the time. I have a lot of other useful information, but I'll try to complete it quickly. So we have this molecule. In this case, we have this this molecule where we introduce a group which generates this AI behavior, but we use it as a co-monomer unit along with the polymer. I'll skip this, and irrespective of the ratio of water, they are very, very bright fluorescent. This is what I showed in the introduction slide also, that these molecules are excellent molecules, that whether they are organics or solvents or even in the presence of water, they remain bright. Okay, so they are dual state emitting materials. A lot of applications are possible in electronic industry and in the healthcare industry. So due to lack of time, I'm skipping that. So here again, we have made a copolymer. So both this copolymerizing unit, in this case, you have thiophene, which is directly attached to this compound, whereas in this case, you have a phenyl bridge in between them. Okay, so both the compounds we have used along with this polyfluorine polymer, and we have made these materials, and we have fabricated these LED devices in our lab. And if you see in this case, both these materials, I'll just request your attention in the middle part. We get this CIE coordinates of 0.31 and 0.33. In this case, it's 0.35 and 0.34. And you can see the entire spectrum is covered. That's what is the reason for this beautiful this white light. I'll show you the real devices. The brightness of this device is also very, very high, around close to more than 9,000 candela per meter square. With the phenyl group that is there, and with the directly thiophene linkage, we get around 7,500. And the efficiency is also very high, close to 8 candela per ampere. And in this case, is around 5 candela per ampere. And these are the real devices with this kind of materials. You can see the white light that is coming out of the LED. So you can fabricate this LED these devices in the lab with this single polymer. So the single polymer white light emitting devices is a very important challenge which we could overcome there. I'll briefly touch upon few other the AI based polymers. So in this case again, when you have polyfluorine, usually whenever it's an organic solvent, it gives blue light, but whenever we increase the ratio of water, it turns to nanoparticles and it becomes red color due to aggregation. Okay, and of course we have shown their use in cancer cell, various kind of cancer cells applications, and few other bioimaging also that you can see here in the red color and the bluish green color. And it gives very nice morphology and also in a cancer curing. Okay, I move ahead to another set of molecules. Here also you have the same thing. You interact. You have the same molecule. We change the functional group, and we have a very similar application, both in the imaging as well as for the cancer therapy. In this case, we have extended the application of this kind of systems for even curing the cancer, the tumors in the mice model. Okay, so this is a very, very important application. You have this various kind of color, the green and the red color, and the tumor curing is also possible. We can also deliver the doxorubicin drug along with this. So it is used for a multimodal application for imaging, for cancer cell treatment, and also for drug delivery. Okay, so it's an application for very, very for multiple things in the field of sensing as well as for biological thing. We have also used a similar molecule for Alzheimer's disease. Here again, one of the challenges that remains is to cross the blood-brain barrier. And in this case, we make the polymer, very similar polymer that I showed, and we have shown how we can disaggregate the aggregated peptide. Okay, we can reduce the amyloid toxicity, and the reactive oxygen species that are generated, that can also be prevented. And the mouse that is there, it can be cured, with this aggregated peptide, or from Alzheimer's disease. So we have also shown this. Okay, so those interested can go through the publications, the recent publications, that reported below. I think, I have some very interesting results, but anyway, I'll just briefly touch upon them. We have made some devices, and we have also transferred the technology to industry. This is a field effect transistor devices, where we can detect and distinguish between gram positive and gram negative bacteria using this OFET device. And this is a very interesting problem. We can also make flexible devices with this, and we have transferred that to the industry, and industry is already making these prototype devices. Okay, which probably we were planning to have come out in the market in this year, but due to pandemic, we had some other things to do, and we could not complete this. But this is a prototype device, that might come out to detect various kind of microorganisms, because it's a very important development that has happened along with the industry. It's a portable kit, and we have now extended this device even to detect various kind of viruses. Okay, and while this work was on, in the month of March, we also had this pandemic, and with the same thing, we got a lot of this media coverage. I'll skip this slide, and we were also able to generate this COVID detection kit at IIT Guwahati. Okay, so yeah, I'm almost at the end. So we also could make this COVID detection kit, and all the 3 basic kits that are required for this COVID detection: the viral transport media, the viral RNA extraction kit, and the RT-PCR kit. You can see all these are manufactured and developed at IIT Guwahati with our industry partner. And it was a very big help to the state government, and now we are supplying to almost all across the country all these kits for the detection, or for transport of this virus anywhere. Okay, and of course this was got a lot of media attention, also got a lot of praise from the ministry. And you can see here, even the Prime Minister's office had tweeted this in the Man Ki Baat program. Okay, in addition to that, the Ministry of Education and also our Education Minister, Dr. Ramesh Pokhriyal, they have tweeted it. And IIT Guwahati and RR Animal Healthcare, they have got a lot of this appreciation for this timely help that you have made to the society. So I move ahead. So this is the summary of my my work. As such, we have been able to generate. I hope the students are convinced that we have by tuning these molecules, you can really have a lot of different applications in the area of this fluorescence, and in the chemical sensing, biological sensing, and healthcare applications. We can also use them for LED applications, and of course various kind of diseases, especially cancer, and this amyloid disaggregation or prevention of this aggregated amyloid. And these are my students who have been involved in this work. Of course, I showed the entire group in the earlier slide, and it's very heartening that students are so dedicated, and we are able to do some chemistry, and of course extend their application to various other areas. Okay, and of course we have this collaborators from IIT Guwahati, from GNRC Hospital, who provided a lot of help in terms of the CSS cerebrospinal fluid sample and the blood serum samples. And my collaborators are there: Professor Siddharth Ghosh, Professor Sachin Kumar, Professor Patra, and a few other collaborators from other institutes. We use these facilities at IIT Guwahati, and funding agency from DST, the Department of Information Technology, and Max Planck Institute, along with DST for this funding. Okay, so I am also part of this journals in the editorial board. So it's my duty to also invite submissions. So from January 2021, I will also be part of the editorial board of ACS Censors. So they say, tell me to advertise in various meetings. So I invite you all to also submit your papers to ACS Censors. It's a new upcoming journal already. Very high impact, close to 7 impact. It is there. Also part of 2 other journals is ACS Applied by Nanomaterials and ACS Applied Biomaterials. So this is another invitation for you all to consider your submitting your work to these journals. Okay, so this is all I have to say. Thank you very much, Orissa Chemical Society, for inviting me and for this interaction and this presentation. These are IIT Guwahati campus. We have a lot of birds coming inside our campus. We have migratory birds, lot of lakes, and beautiful campus. Hopefully, things will become safer. You all will be able to travel. And if you come this side, please don't hesitate to call us. In addition to me, Professor Aditya Panda is also giving a talk tomorrow. from IIT Guwahati, and I can see a lot of other former IIT Guwahati students, Francis and Rupam, also as speakers here. So I'm sure that, you know, it will be a great opportunity to welcome you all to IIT Guwahati campus and interact with us. With that few words, I thank the organizers for this opportunity to present our work with you all. Thank you very much.
Thank you, Professor Iyer, for delivering your talk on nanomaterials, which are very burning materials nowadays. And also you have touched the fluorescent sensor and also induced emission and also many applications. And I hope my students, all the delegates will be educated from your deliberation. Thank you. Thank you a lot.
Thank you, madam.
There is just one question. There is just one question from a speaker to the speaker from Kanhu Charan Behra. Can these sensory molecules be converted to wearable sensor or can be converted into electronic devices?
Yeah, but this is a very good question and also a very relevant question in the present context. In fact, you know, we are working on wearable devices. Already we have made a lot of electronic devices. I have shown on the memory devices and LED devices. But of course, you know, the main purpose of making these molecules is to convert it to sensors which can be taken in a remote place. And for that, you know, it has to be both portable and of course wearable. Okay, so this is a very interesting question, very important question. And the answer is yes. Yeah, it can be done.
Thank you. Madam.
Thank you.
The second speaker is Dr. S.K. Sahu. He is the Associate Professor of National Institute of Technology, Surat. Received PhD from Punjab Technical University, Jalandhar. He received many awards, recognitions, and fellowships. He is a principal investigator of many projects. He has many research publications to his credit. His interest of research is manifold. He delivered invited talks in many institutes. With this CV, I just introduced Professor Sahu and request him to present his talk within the time. Dr. Sahu, please.
Thank you for the nice introductions. Can you hear me?
Yes.
Yes, yes.
Yeah. Can you allow to share my presentation?
Professor Iyer, please unshare your slides.
Yeah, I'm unsharing it.
Yes.
So first,
Devices, please stop one. Two devices running. Okay. So, Professor Iyer, to kindly.
I am doing that only. It's taking a little time.
Okay. Okay, no problem. Take your time, please. Yeah, that's done. Now, Professor Sahu can share.
Professor Sahu, please tell your screen name so that I can make you co-host. Professor Sahu?
Yeah.
What is your screen name?
Dr. Subhan K. Sahu.
No, there is another you can use.
Which one you are now using? Because he wants to
one
that. Sorry?
Co-hosting not necessary, you can continue.
Yeah,
No,
office,
sir.
I think I have written. Huh?
You cannot share the screen, sir. Okay, I got it.
Yeah.
Yeah, now you can proceed.
No, not.
Now you are the co-host, Dr. Sahu. You can now share your PowerPoint file.
Yeah. Now I joined with two login ID. Okay, I want to share with my desktop. Okay, that is office, I think.
Then tell the name, sir.
What
is the login ID of that?
Login name. Then
login name.
This is office, it is written. Office.
Office, okay.
Yeah.
Can you search office?
Yes, okay, yeah.
Got it?
Got it.
Okay.
Okay, done, sir. You can now.
Office is now co-host, please share the.
Yeah, thank you.
Yes, thank you. Nicely done. Yes. Madam, kindly put Professor South's time. We give him 30 minutes. Madam.
Okay, thank you.
Yes, okay.
Okay, I will try to complete my talk within 30 minutes, and my talk will be also very similar to the Professor Ayer's given, but my talk will be more on the aggregation induced emissions. Okay, so whatever the sensors we have developed this year during this COVID period, that sensors we are going to discuss in this presentation. So the outlines of my presentation will be first, I will discuss about some fundamental about the fluorescence sensing. Then I will discuss about the aggregation induced emissions and some of the applications that we have done with the organic system as well as the inorganic nanomaterials in the field of sensing with aggregation induced emission mechanism. Okay, so first of all, we have to understand this what is a fluorescence sensor, how you can design a fluorescence sensor. Okay, so generally in a fluorescence sensors, you can have three important parts, three important things you can say. One is the reporter unit, that is your light emitting unit or a fluorophore or a optically active nanomaterials. And that optically active nanomaterial or the organic fluorophore must be connected with a binding site which will selectively recognize your target analyte. Once the analytes interact on the recognition site, then a mechanism is some mechanism is occurred, and the fluorescence properties of your fluorophore or maybe the your nanomaterial is changed. Okay, so fluorescence sensors generally have three important things. One is your fluorophore, and one other is your binding sites, and third is the sensing mechanism. Okay, there are so many different type of sensing mechanisms are there, just like PET, freight, ESIPT, okay, excimer based fluorescence sensors. So this mechanism, once the analytes is interact on the binding site, this mechanism get activated and it changes the your fluorescence properties of your signaling unit. So whenever if you are designing a fluorescence sensors, you have to, there are different way you can categorize the sensors. Okay, here you can your fluorophore and your binding site, they may be connected in a integrated form. There will be no space between them. Okay, that is integrated system, or your fluorophore and the binding site may be connected through some spacer, some group. Okay, they are separated by some group. So this is, you can say, the integrated system, and this is a spacer system, reporter, spacer, and the binding sites. Okay, whenever it will interact with the analyte, it should change some fluorescence. Okay, there are third type and the fourth types are also there. In the third type, your sensors may interact with your target analytes and it form a new product, that is a reaction based you can sensor, or we can call as a chemodosimeter. And in the fourth type, the fluorophore and the binding site, they are weakly interacted each other by some non-covalent interaction. Okay, because of the high affinity of the binding site with the analyte, the binding site will be comes out and your fluorophore will be free. This is the indicator displacement approach. Okay, so we have made so many review in the recent past, and these fluorescence sensors, because of the high affinity, high selectivity and sensitivity, these are and low cost especially. Okay, it has a wide application in a diversified field, especially in the biological, environmental, analytical field. These fluorescence sensing are widely applied. Okay, so in our laboratories, we are generally using these, we are modifying these vitamin B6 cofactor, and we are using these vitamin B6 cofactors as a binding site for designing different kind of your chemosensor or nanosensors. Okay, you can see that these are your biologically active cofactors. Okay, and these are active from, they play so many transformation, and we are using these cofactors. This is pyridoxal phosphate, pyridoxamine. These molecules we are using as a binding site, and we are connecting this molecule with different type of fluorophore and the nanomaterials to design different kind of your fluorescent sensors. Okay, one of these examples I want to explain here, that in order to explain you about the design of a fluorescent sensor, you can see that here this is the sensors, that is Tornon sensor for the zinc metal ions. Okay, and here it contains a pyrene fluorophore. It connected to the your pyridoxal unit. Okay, so this is the recognition side, this pyridoxal, and this your pyrene act as a fluorophore or signaling unit. When zinc is added to this system, okay, it forms a complex in 1:2 ratio. Once the complex is formed, the two pyrene molecules come closer and form a pi-pi stacking interaction, and this is called excimer formation. Okay, because of this excimer formation, you get a new fluorescent band, red shifted fluorescent band. Okay, this is because of the your excimer formation. So you can see that this system contains three things. One is your fluorophore, here pyrene, and this pyridoxal act as a recognition site, and this mechanism, that is excimer formations, that act as a, that mechanism gives you the signal that can be used for the identification of your target analytes. Okay, so there are so many other experiments, spectra, selectivity curves. This is titration that are performed for identifying to determine their selectivity and sensitivity of these sensors. Okay, so I think so all of you have understand about the fluorescence sensor. The first speaker also speak a lot of, about these sensors. Okay, so I think they also explain about the aggregation induced emission. This is one of the most new type of mechanism that is widely applied in the field of the sensing and the biosensing. Okay, this aggregation induced emissions, this mechanism was first identified in the 2001, and now it become a hot area, research area, and it is widely applied in the different type of field in addition to the sensing and the biosensing. So generally, you know that fluorescence generally, it is very concentrate, if you make concentrate, generally it undergoes quenching. Okay, if you see the example of the fluorescent, it is highly fluorescent, but if you increase the concentration, that aggregation cause the fluorescence quenching. This is called the aggregation cause quenching. But there is a opposite mechanism. If you increase this concentration of a molecule, it will stop the free rotation of that molecules. Okay, and it causes a fluorescent enhancement. Okay, this is we call as a aggregation induced emission. Generally, when your molecules, which is freely moving and has a ability to form multiple conformation, when it is singly present in the solution, then when you excite that molecule, because of the deactivation, okay, collision with the molecules or multiple conformation, generally in the singly formed molecules, they are become a non-fluorescent condition. But if you aggregate these molecules and stop these molecular rotations, then it will start to give your fluorescence. Okay, this is what we call as a aggregation induced emission. And this is very easy to prepare this type of sensors. So this mechanism is now widely applied in the field of the sensing. Okay, so we have developed a very simple molecules in our laboratories. Okay, if you see this is a very simple chip base, which is planar in structure. Okay, and there is a two pyridoxals we need, which is connected with your hydrogen. Okay, very simple molecule. There is no need of any inert environments or many robust facilities for synthesizing such molecule. These molecules, when you take in the DMSO, it become, because in DMSO it is freely soluble. Okay, in DMSO it is freely soluble, so it is in the singly form. So these molecule have a many rotations, so it is non-fluorescent in conditions. Okay, when you added a poor solvent where this molecule is not soluble, just like water, when you added the water into the DMSO, when you increase the water percentage, you can see that there is a slowly the fluorescence is enhanced in the red region. Okay, red emission is occurred. This red emission is occurred because when you added the poor solvent, these molecules started aggregation. Okay, they form a needle-like aggregations, and this is also supported by some DLS data. And because of this aggregation, it will start to give the red emissions. Okay, so in a simple step, applying the aggregation induced emission, you can have a simple non-fluorescent, we can convert it into a red emitting your chip base. And this chip base molecule, we have tried to change the pH of this aggregate solution. And you can see this, there are 3 pH window. In the acidic condition, it is non-fluorescent. When it is in the 6 to 10, it giving a red fluorescence. And when it is in the basic condition, it will started giving your green fluorescence. So you know that there is a need of a pH sensor which can be useful in identifying the pH of in the cellular level, because they are electrode, you cannot use it. So this simple molecule, we can use as a pH sensor which shows 3 windows pH behavior. In the acidic, it will be non-fluorescent. In the 6 to 10, it will be reddish, and then in the higher pH, when the OH group are deprotonated, they become green fluorescent. Okay, so we have performed a titration to determine what is the pK of this chip base, and how the molecules behave with the change in the pH. And you can see that you can use this pH, these simple molecules, to monitor a ratiometric pH sensor for the neutral and the basic pH. And these are some of the computational calculations, DFT based calculation we have performed in our laboratory, that how this aggregation takes place. If you see this DFT computed structure of this molecule, there is a intramolecular hydrogen bondings, and the structure is planar in nature. When the number of molecules are aggregating close to each other, that molecules are forming some intermolecular hydrogen bonding between the molecules. So that helps in making the aggregate, self-aggregate in a stable form. And we also perform a non-covalent interaction, and these green shade in between indicate the electron densities that helps to helps to make the attractive forces between the molecules. So these are the computational evidence supported that this planar type of chip base can also undergo aggregation, and it will give you a nice fluorescence that you can apply for different kind of application, including here we have tried for pH sensing. Okay, in addition to this application, pH sensing, we have tried to apply this aggregated solution in identifying the latent fingerprints. You know that in the forensic science, these thumb impressions are widely used for solving so many criminal cases. Our simple chemistry can help them to identify these different level of these fingerprints. Okay, and you can see that we have taken the thumb impression on the glass surface. Okay, and then the aggregated solution was just kept for 5 minutes and just decanted. After drying, we have taken the image, and you see that these aggregate particles are observed on the ridge of that thumb impression, and we can see the nice image of these thumbs. This is the 4 different research scholars. They have given the thumb impression voluntarily, and we can identify the different thumb impressions of the 4 persons separately within this simple molecule. So this don't need any kind of sophisticated laboratory facilities, that you just a simple molecule that you can apply the aggregation induced emission mechanism, and you can go for the diversified applications. Okay. This is again a simple molecules, not you can see that this is also, this work is also published during this pandemic time. Okay, and you can see that this is a simple one-step reaction with a paradoxal with a 2-amino-thiophenol. It is a one-step reaction, and you get this simple chip-based molecule. And I think this type of reaction are routinely done in the college level also. It is just our moieties are different. Okay, and this simple molecule, this paradoxal, and this molecule is freely rotating if you are dissolved in a good solvent like DMSO or some organic solvent where these molecules are freely solvent. So that's why these molecules are freely, this molecule is non-fluorescent in nature in DMSO. When we add water, the poor solvent, then these molecules started to aggregation. You can see that in the DMSO it is non-fluorescent. In the right side you can see. And when you increase the DMSO in water percentage, then it started to give the fluorescence. This is because of your aggregation induced emission. Some theoretical Dept calculation was done to support that why this aggregation is takes place by this simple molecule. And then we go for this pH sensing. And similar to the previous molecule, this molecule also showed these red to green emissions from a neutral region to the basic region. So these molecules, these simple molecules also can be applied for the sensing of the pH, and you don't need to go for a robust synthesis. Okay. So this is new applications. This is the work that is going on in my laboratories now. Here we have synthesized simple molecules. Okay, simple chip-based molecules, and these chip-based molecule we have applied for the sensing of the copper, and this fluorescence is quenched by the copper, and then we converted this turn-off sensing into a ratiometric sensing by using a reference dye. Okay, using a reference dye fluorescein. Okay, if you see this scheme of the sensing of the copper, this chip-based molecule, the structure is shown here. Okay, it is synthesized. This is a flat molecule. So this molecule shows your aggregation induced emissions. Okay, it will show the red emission. When you add the copper, it is quench. Okay, so and that turn-up sensor was converted into a ratiometric sensor by adding a reference dye, that is fluorescent. I will show you how this turn-up to ratiometric sensing was done. Okay, you see this. That molecule gives the red fluorescence at around 600 nanometer. Okay, when you added different metal ion, only copper gives the copper quench the fluorescence. So there are so many other experiments we have performed and to determine the sensitivity, and this chip base is act as a fluorescence quencher for the detection of the copper. Okay, so there are other experiments we have performed and we apply for real sample analysis also. Okay, and what we did in this red color emission aggregate, we added a green dye as a reference. Okay, the green fluorescent dye we have added. Okay, and they showed two fluorescence. One is your red fluorescence due to your that is aggregation induced emission, and another fluorescence due to the fluorescence. So there are two fluorescence. This fluorescence is in it is a reference dyes. It is not interact with the your copper. So, but your aggregation induced is active towards copper. So when we added, you can see that there are two emission here. This is for the AI active molecules and this is for the fluorescence. Okay, so when we added copper to this aggregation induced emission is quench. Okay, but this become your remain silent because this is used as a reference. So we can see that green fluorescence here. So a turn-up sensor is converted into a ratiometric sensor, and we perform this some titration also performed to determine your sensitivities for this reaction and apply this for the different kind of the water samples. Okay, that is biological sample for the detection of copper. Okay, you know that whenever you are designing fluorescence sensor, your fluorophore may be that light emitting unit may be a organic fluorophore, or it may be a optically active nanoparticles. You know that there are so many optically active nanomaterials are there. They showed good fluorescence as well as the color. Okay, some of the examples are shown here, just like your semiconductor quantum dot, fluorescent nanocluster, peroxide nanoparticles. These are also the surface of this nanomaterial can be modified, and you can prepare, you can develop so many sensors. Okay, and these nanomaterials also apply for the designing of aggregation induced emissions. Okay, so I will show you first. I will show you some of these gold-based nanomaterials, how they are applied. Simple examples. These are some. This is a gold-based nanoparticles. Functionalize. It shows red color. Okay, red color, and here you can functionalize the pyridoxal derivatives on this surface. Okay, this red color, when you add the metals, you can see that the free nanoparticles, they get close to each other, aggregation. And aggregation of the nanoparticles change the optical property. You know, nanoparticle are size, their optical properties are size dependent. When you add the analytes, if the nanoparticles come closer, the size dependent properties change the optical property. Okay, so here the red color gold nanoparticles, that is become, when you add chromium, it is changed into a blue purple color because of the complexation induced that is aggregation of the gold nanoparticles. So this is what the color is changing because of the aggregation. Here I am going to explain about how the emission is changed because of the aggregation. Okay, this is just a example that nanomaterials are also sensitive to the aggregations. Okay, these are some of our previous work on the color-based sensors. Anybody interested can go through our published work. And you know that there is a new type of when you your fluorescent nanomaterial is apply in the field, that is fluorescent nanoclusters. When you decrease the size of the nanoparticles, your gold, silver, copper, to a ultra small size, that is few to 100, it contains 3 to 100 atoms, and size should be less than 3 nanometers. So,
Dr. Sahu, may I request you to close your talk within 5 minutes?
I'm just within 5 minutes. I'm just closing my talk.
Thank you.
Okay. So this will gives you a beautiful fluorescence if you can decrease the size of the nanoparticles, and you know they are very good photoluminescence, photostability, good compatibility, and these these nanomaterial also widely applied in the different type of field. Okay, and this synthetic procedure is very easy. Okay, you can you know copper is available in every lab. Simple reduction of copper, you can prepare a copper fluorescent copper nanocluster, and I will show you that a simple copper salt taken from my lab that we have developed a red emitting copper nanoclusters. Okay, this is the scheme. We have taken copper sulfate and we have used a glutathione. This will reduce the copper ions into copper, and we have added some beta cyclodestin. Okay, that will act as a that will decorated on the surface, which can be used for inclusion complexation. This work is under revision now from the SES applied nanomaterial. So this red color emission, you can see that this copper, you can see that is giving a beautiful red emissions in a very, if you add NaOH onto copper in presence of GSH and beta CD, it will gives you the red emitting nanoclusters. And then we added different vitamin B6 cofactor. The addition of PLP form a inclusion complexation on the surface. Okay, inclusion complexation form, and this will change the red emission nanocluster into green color. Okay, this allow to, you can detect PLP also. Okay, and then we added aluminum. When aluminum is added, these nanoclusters come closer and you get a blue to green fluorescence because of this aggregation of these nanoclusters. Okay, so this is how this some of the experimental evidence that how this inclusion complexation takes place on the surface. Some evidence we have taken, and the titration that how the red nanocluster is converting into your bluish green with the addition of the your pyridoxal. Okay, and this is how the addition of this aluminum into that is self-assembled of this PLP and the copper nanocluster. You can see that there is an enhancement in the fluorescence. Okay, this is nothing but your aggregation induced emissions. Okay, and these are some of the others. This is specific competing experiment, and this is the DLS. DLS is giving evidence that the nanoclusters are, the size of the nanocluster is enhancing because of the aggregation induced emissions. Okay. So this is some of this titration to determine the aluminum, the sensitivity and some applications. Okay, this work is under revision and we'll going to submit very soon. I think this is my last slides. Thank you. If anyone have questions, and there is a online conference in my department. Anybody can wish to join. there are speakers from the Nobel laureates J.M. Lane going to speak. There are several awards from the RSC and SCS. And also there is a membership fees to all the participants. And the proceeding will be published in the material today, proceeding. Anybody wish to join, the website is there, or you can contact me. Okay, thank you. If you have any questions, you are free to ask. Thank you very much. Thank you, OCS. Being a Odia, I am very much thankful to all my Odia family. Okay, I am in Surat, but I'm always in touch with OCS, Orissa Chemical Society. Thank you very much.
Thank you, Dr. Sahu, for your deliberation on fluorescent sensors, its designs and applications. You mainly focused on fluorescent sensors based on aggregation of induced emission. Once again, I thank you for your nice deliberation. Thank you. Thank you.
Thank you.
There is just one question from somebody. The question is this: how the fluorescence lifetime changes as a result of aggregation-induced emission?
Yes.
This is a question.
Yeah.
One from the audience: how the fluorescence lifetime changes as a result of aggregation-induced emission?
Yeah, lifetimes it will obviously change because the molecular rotation is changing. Okay, and when it is aggregated, the fluorescence is changing. So generally, when the aggregations, the lifetime should change, it should enhance. But generally, in our work, we have not performed any lifetime experiment. Okay, so that's why in our molecular case, I cannot say what is happen with the lifetime.
Madam.
Now I invite Dr. Rupam Sharma, University of Kentucky, Lexington, USA. I am extremely happy that you have joined from such a long distance, USA. Now I invite Dr. Sharma to deliver his talk.
Is title of the lecture, Madam?
Title of the lecture.
Bio-inspired membranes application towards pollutant degradation and value-added transformation.
Yes.
Hi, can you hear me?
Yes.
Yes, yes.
Okay, yeah. I'm gonna turn off my video and share my screen, if you'd allow me to do that. So.
Before that, could you please tell the local time in your place?
Oh, it's 2 a.m. in the morning.
Oh, damn.
Almost 2 a.m. 1:56.
I have made you the co-host. You can share your slides, sir.
Oh, okay. Thank you very much.
Let me go through his biodata.
Yes, sir.
Rupam Sharma is a scientist too in Department of Pharmaceutical Science, University of Kentucky, USA. He received a PhD from IIT Guwahati, India. He has a good number of research publications to his credit. Dr. Sharma attended many symposiums and conferences in USA. He received the DST Inspired Faculty Award, Government of India in 2015. He stood first class first and received gold medal in chemistry from Guwahati University in 2006. Now I request Dr. Sharma to present his deliberation. Dr. Sharma, please.
Madam, we have 25 minutes.
Oh, sure.
Time is 25
sorry?
minutes.
Oh, yeah. Okay. Thank you. Thank you, Dr. Lanka, for the introduction and Orissa Chemical Society to give me the opportunity for presenting my work. Yeah, I will be talking about some I think a little bit unconventional chemistry here in terms of membranes mostly. It's a little bit more applied and more towards chemical engineering than basic chemistry. But I'm from basic chemistry background, so my intake here is chemistry. So I'm trying to say something more about chemistry than the engineering part. Now, before I actually start about the membranes, I want to dedicate a few slides to my dear student, student friends there who are listening to my talk. So, chemistry is found everywhere, and you all know that, and it has got immense application everywhere: energy, medicine, separation, forensic, whatever, you just name it. Now, during our MS or PS days, basically we struggle to, think about like, okay, whether I should go for inorganic or organic or, physical chemistry. But I think this is my perspective, and probably others will also agree that it doesn't matter. Once you are in the system of chemistry, it's so diverse these days, and interconnected, that you get those applications everywhere. And that's how I went through my career. I started my career working on MOFs for use as storage materials in catalysis separations. Then I worked on mainly catalysis. From the experience of synthetic chemistry, I developed different catalysts based on, organometallic compounds, and used it for renewable energy or water oxidation, all those type of things. Then, with the background of again catalysis, I moved forward to another research area, which is enzymatic catalysis, and applied those enzymatic catalysis towards, membrane fabrications. And later on, I actually currently working in the pharmaceutical sciences department for bioanalytical works. So, and what I'm going to tell you is, in the heart of all these chemistry is analytical chemistry. And I really request you to give a little bit more stress on analytical part of your knowledge, so that you can, connect all the chemistry together, have sound knowledge and the chemistry with your analytical techniques as well. I just like to say that this is the IT of chemistry. Once you have the analytical chemistry on your hand, you can definitely excel. Now, let me go to my actual, part of the presentation. I'm going to talk about the membrane, some bio-inspired membranes. Those uses the enzymatic catalysis part from the chemistry. Now, the bio-inspired membranes, why we call it as bio-inspired is basically the inspiration comes from nature, right? Our natural membranes are full of lipid bilayers, and then it has those proteins in it who is kind of like the selective things that allows a few selective materials to go in or out and restricts the others. And inspired by that type of a phenomenon from the nature, and we all actually inspired by nature from all the time. So these completely synthetic membranes are developed, and they are mostly polymeric based materials. And then the pores are, you can just design the pores based on different criteria and needs. And these bio-inspired membranes, the so-called bio-inspired membranes, are mostly, those pores are in the fabricated with some ideas from the bio, maybe a protein channel, maybe enzymatic channel. So it's just the needs, and then you can develop a membrane. Now, why we are talking about these membranes? Definitely we need a problem, and then we need to go for the solution. And that's why we are talking about these membranes to solve some kind of a problem. And the problem I'm talking about today is, the chlorinated organics. In our day-to-day life, we have we have seen so many different compounds. We are definitely seeing these use of these compounds like plastic materials or our pens or pesticides, and all of these different type of uses got help from the chlorinated organics. Basically, these chlorinated organics may be some chlorophenols, maybe some chloro alkanes. They have got their importance as herbicides, pesticides, or different use in wood preservation, etc. and etc. Now I'm going to talk about more about the chlorophenols. They are used basically mostly in insecticides, herbicides, etc. And they have also got applications in leather industry, textile industries, but they are they have got various toxicity, say about carcinogenicity or some immunotoxicity. They are toxic, and because of their toxic nature, different organizations came forward and had to ban some of those or most of those from time to time. Now, for example, these chlorophenols are banned in European countries from almost like 80s, and then USA have banned this trichlorophenols that was used here as herbicides. India also has banned use of polychlorophenols in agriculture and in leather industry, but I believe it's still in use in some other areas. So we need to get some solution, like because it's not a complete ban. So we need to have some kind of solutions towards remediation of these chlorophenols. Now, what might be the solution is because we are chemists, we can talk about different solutions, right? So this one way to just get rid of chlorophenols is to degrade them to less toxic products or more useful products. This is one just a schematic how we can degrade them, and various catalytic pathways are developed from time to time to degrade those type of chlorophenols. And I'm just taking an example of 2,4,6 trichlorophenol as an example here. Okay. And if we go by the literature, I have some surveys here. Almost like 53% of the reported literatures are based on catalytic degradation, and then some are with nanoparticles. And there is a very, it's significant, but not that significant, 10% only based on enzymatic degradation. And so there is opportunity there that we explore more into the enzymatic degradation area. And when we talk about enzymatic degradation, there are problems because these enzymes are expensive. They are time to time not renewable, reusable, and they are very short-lived as well. But then there are plus points that they are very selective because it's natural, right? So they have very high activity compared to any other catalyst. They are the best catalyst in the world, right? So they have got their positive, they got their negative. Now, as a chemist, what we should do, we can always use those positive things, and they will be there because it's inherent to them. And then the negative ones, if we can just somehow manipulate those enzymes to be more reusable, then more not activity wise, but more robust, so that it can be used for longer time. So that's what our goal is. And that's where the enzyme immobilization comes into play, right? So enzyme immobilization is a technique where you bind the enzymes to other substrate, and then still you get the similar activity, but more durability. That's how it is. And in the past 30 years or so, there is so much interest on that area, like enzyme immobilization. And if we talk more specifically about enzyme immobilization on membranes, then again, in the last 20 years, there is like in 20 or 30 years, there is growing opportunities and interest on that area. And when we talk about enzyme immobilization, and particularly in the membranes, and again, I'm talking about synthetic membranes, just like our filter papers that we use in the laboratories, right? So there are various approaches to do that. You can do covalent modification, you can do just electrostatic modification, or entrapping the enzymes into the pores of the membranes. Here, what I'm gonna talk about is an approach which is called a layer by layer assembly. Here, basically, it's not a covalent modification. There are issues with covalent modifications because something is covalently bound to the surface or to the pores. You cannot again go back to that membrane to do something like a reusable membranes. But if you do it non-covalently, then you can always, there is a possibility that you can always use them as a reusable membrane, So what I'm going to talk about here is a reusable kind of membrane, and the technique used here is called the layer by layer assembly. And this technique is basically you take the membrane, which is a PVDF membrane, polyvinylidene difluoride membrane, very robust membrane and cheap also, and then we polymerize it with a polyacrylic acid polymerization to get some carboxyl units there. Again, the idea is not covalently bound enzyme here, but we can do definitely some covalent modification to the membrane without having covalent bonding to our target is to have the enzymes there electrostatically bound, but not covalently bound. But someone might question, you did a covalent modification just right there, but no, what we are talking about, it's the enzyme that we do not want covalently bound, but other units we need to have some carboxyl units there or other functional units there to have a good binding to the enzyme. So the first step is the carboxylate units coming there. Then the second step and onwards, it is the electrostatic interaction. Now, by nature, this lacase enzyme right here is a negatively charged enzyme. So for having to have a electrostatic interaction, we need something positively charged. So we introduce polyalyl cations there, and that binds to the negative ion, and then that makes the platform for my lacase enzymes. And then comes the lacase enzymes, and that will get trapped, and then electrostatically bound to the membrane pores. That's the basic idea of the layer by layer assembly, basically electrostatic interaction of counter anions. And if we go by statistics again, then there are like up to around, this is until around 2018, there were like 594 records of layer by layer assemblies on membrane. And again, this 594 is, I think, is a very low number, and there are opportunities in that area. There is. Let me introduce you to the lacase enzyme a little bit. Why we choose that? It's one of the versatile enzyme in the in the field of degradation or catalysis of chlorophenols or any chloroorganics. It is a copper-based enzyme. It's very versatile, as I already told you. It has got application towards lignin degradation, and it's well known. Okay, and price-wise also, if we talk about the cost, it's relatively cheaper. It's microorganism-based one, right? So someone can just if we do not want to go to Aldrich or Fisher Scientific, then someone can produce it in lab in very cheap cost. So it's a very good one for those type of remediation studies, and there are a lot of reports on that. let us talk about the results, how we proceeded and what we got. So this is the framework. The very first one is this is the framework of a PVDF membrane, and then we modified it to have some carboxyl units, and later on with the polyalyl amine units electrostatically bound to the carboxyl unit, and we characterized them with FTIR, and step by step we could get the signals from the functional materials that we were targeting there. Then we also check the contact angle. So for membranes or any type of surface behavior, contact angle is a very important one. This PVDF material is a hydrophobic material. So, and by nature of the hydrophobicity, it will have a very high contact angle. And then because we immobilized our carboxyl units into the membrane, that makes it hydrophilic, somewhat hydrophilic, I would say. So, and it will lower the contact angle. Okay, but later on, think about it, that the pores or the surface that we modified with the polyacrylic acid units, it's so huge that you will definitely see that change of 80 to 56, and it already got the electrophilic nature. But then later on, when we functionalize with polyalylamide hydrochloride and with the enzyme, the amount of the enzyme added there is not that much. It's nowhere compared to the polyacrylic acid. So there is no drastic change here, and you will not expect that drastic change because of the hydrophobicity offered by the protein part as well, right? So, but it's just there. It's not going back to the previous hydrophobicity, but it's just there and sufficient for our experiments. And we also tracked the functional groups again from the characterization standpoint with XPS. We saw the anticipated amide groups there, or amine groups there, which confirms our the immobilizations. We did some SEM images. Here are the bare PVDF membranes that has the pores here are somewhere around the range of like 200 nanometer-ish. And then after you immobilize the polyacrylamide, basically it shrinks down the pores to about 120 nanometers, and then followed by the following steps of immobilization. It again blocks some of the pores, and then you get the other pores to be shrinked by under 50 nanometer or so. So you get membranes with 70 nanometer pore areas. Those are very good microfiltration membranes. And I'm going to talk about some of the immobilization and then the activity of the enzyme. We track the activities of those enzymes, before immobilization, and or that's basically the solute phase, versus the after immobilization, which is the now immobilized membranes. Immobilized enzymes on the membranes. So if we compare, and those are Michaelis Menten fit. So if we compare their KCAT, which is the activity of the enzymes, they are very comparable. If we talk about the free versus the immobilized, they are very comparable. So the activity, in terms of activity, we didn't lose anything. But if you see the Km values, which are actually the binding property of the enzyme to the substrate, now we lost some of the binding properties, and which is anticipated now, because under free, the substrate can directly go and bind to the active site of the enzyme. But when it is attached to some other substrate, in the immobilized case, so you do not get, or the substrate do not get all the active sites. It do not get the chance to directly go there and then bind to the active site. So we lost some of that, but that's okay. We can tell that that's okay. We lost some of the property of the enzyme, but then we gain somewhere else. Where we gain, we'll talk about it in a minute. Now, first, I want to tell you the reaction aspect. So that's where we start with the trichlorophenol as our model compound. And after reacting with our membrane reactor, passing through the membrane reactor, what we got is a dichloro quinone compound. If somebody asked me that, okay, I give you a water with trichlorophenol, I know that's toxic, but now you get water with, dichloroquinone. Will you eat now? Will you drink it? We'll say no. This is not, I'm not claiming it to be like non-toxic, but what I can tell you, this is less toxic than the trichlorophenol. At least we can, partially deal with the problem, not completely, for sure. And efforts are going on, probably, if not in our laboratories, but other laboratories, to deal with such problems. Now, and again, we also saw some other materials, not only this dichloroquinone compound, but some hydroxyquinone compound as well. And we tracked it with UVVs. My analysis were based on HPLC analysis mostly, so this is a profile how the membrane reacted towards degradation of trichlorophenyl, and in case of membranes, it's everything is with respect to the flux of the membrane, right? Now, and we can actually change the flux based on the pressure we applied towards the feed. Now, activity of the membrane will be a factor of that flux or the pressure we deliver to the feed. And here you can see that more than 80% or close to 85% degradation we can get at optimum 2 LMH, which is liter per meter square per hour, flux. And even if we go for a very high flux, high flux, still we get more than 60% of that degradation, which is very impressive, I will tell you. Again, we are not talking about a solution phase reaction where all the materials are there for 24 hours. Here, the feed is going through the membrane for maybe a fraction of a second, and then it's passing through the membrane, and we are getting, like, say, 80% degradation. There is always a possibility that you basically refilter the substrate again if you want to get 100% of your what is that called, the degradation. But it will never be 100% if you go by the theoretical calculation.
Sharma, please.
Sorry?
May I request you to wind up your talk within 5 minutes?
Yeah, sure. Yeah, I'll be done in 5 minutes. Thank you.
Thank you.
Yeah. So that's how the flux behavior can change everything here. But we got like more than 80% of the degradation. Now, when I promised you that I will talk to you something about the stability, we lost some of the binding affinity of the enzyme there, but what we got is the activity. So here is a comparison of the solution phase activity of the enzyme over like, say, almost a month, but not a month, but 22 days or 25 days versus membrane bound enzyme activity. See, the enzyme activity of those membranes were right there, basically in the immobilized case, right there at 100% over the time, but it lost almost 30% or 60% actually dropped in the free version of the enzyme. And we also tested the how many number of cycles we can use those membranes so that we can, so that the reusability of the membrane. And these are the data. It lost only, say, 14% of its initial activity within the 4 cycles, after 4 cycles within 25 days. So that's how it is very actually, impressive results. Now, we actually extended that idea of enzyme immobilization with 1 enzyme there versus 3 enzymes here, which we call a multi-enzyme. Because of the time restrictions, I'm not going to go into details here, but here what we did, we tried to send a message to the community that we can build those type of enzymatic membranes and use it for lignin degradation with multi-enzymatic membranes. And here also we saw more than 90% of degradation of our model compound and reusability of the membranes, over the time of almost like 1 month or so. So that's how we modified our membranes with enzymes, and these are basically bio-inspired membranes. I'm not gonna go into detail. These are just the how the enzymes work there. So in my conclusion, yeah, we have demonstrated some enzyme immobilized membranes with what is called layer by layer technologies. We showed the importance of those technologies towards getting good membranes and good activity for water remediation, and towards lignin model compound degradation. And it has got definitely potential, broad and scale up, importance. And with this, I wanna just thank all of you. I wanna thank my group here. I work for the Center for Membrane Sciences with a big group, and this is the director, who happened to be an Indian guy here, a very renowned person. I would also like to thank the Nanostone, the company we work for. We had a very good collaboration, who provided us the membranes, and KYF score for the money. Thank you. If you have any questions, don't hesitate to just email me, or I bet that there is a time constraint now, but just email me and we can definitely talk about it. Thank you.
One question, with permission of the chair. This is a question from Rabindra Behera. Just curious, how you got similar K-cat value for free and immobilized case with different Vmax? I don't understand the question, but Dr. Sharma, this is for you. Just curious.
Okay, yeah.
Yeah, got it. You got it. Okay.
So K-cat is actually the activity of the enzyme, right? So activity might not be changed with a little bit alteration of its binding pockets, but the Vmax, or the Km, is the binding affinity of the substrate. So the binding affinity of the substrate will definitely get changed with the alteration of its dimensions or the structures with its binding to the other substrate. So there is that possibility for sure, and this is something is in the literature. We have got it, and we got the explanation in there in the paper. You can cite the paper. I have the reference here. SCS Applied Interfaces 2017.
Okay. So I think.
Thank you, Dr. Sharma, for your talk on bio-inspired membrane, which is really very, very interesting. You focused on its application towards pollutant degradation and value-added transformation. Also, modification of a membrane by bonding. Really, it is a challenging field of research. Once again, Dr. Sharma, I thank you to be with us on this Zoom platform from other side of the globe. Thank you. Thank you. Once again, I thank the convener and President Orissa Chemical Society for allowing me to perform this prestigious talk. Thank you all. Thank you.
Thank you, madam. It's a very nice session. First of all, I thank the chairman, Professor Subhasini Lenka, for nicely managing the session. And also I thank our keynote speaker, Professor P.K. Iyer, and invited speaker, and Dr. Professor S.K. Sahu and Upam Sharma for giving new branch of chemistry. It will definitely inspire our students to take chemistry as their career. Thank you all. It's the end of the session 1. Now we will start immediately the technical session 2, in which I request Professor Satyavanjana to chair over the session. Before I handing my mic to Professor Jana, I want to give some brief introduction of him. Professor Satyavanjana obtained his PhD degree in chemistry from Utkal University in the year 1984. He was a postdoc fellow in year 1989 at University of Leeds, UK, and Maxwell's Institute, UK. He was a professor of chemistry at Utkal University from 1999 to 2014. Professor Jana was the head of the Department of Chemistry at Utkal University for 2 terms, that is 2002 to 2004 and 2009 to 2011. 11 students got their PhD degree Working under his supervision, Professor Jena visited China as a mission member of Indian delegation on higher education in year 2010. He was also an academic visitor in the year 2012 to universities in USA like Maryland, Cornell, Rochester, Princeton, MIT, etc. And beside this, Professor Jena is known as the best one of the best organic teachers of Odisha, and we are all fortunate enough to be his students. Thank you. And now I request Professor Jena to take over the session as chairman.
Okay, Devasis, can you hear me?
Yes,
Yes, yes.
Yes, sir. Yes, sir.
Yes, sir.
Okay, so good afternoon to you all. So it is my pleasure to chair this session, and the two speakers happen to be my direct students. It is a pleasure on the part of a teacher to chair a session when the students are speaking. Saroj Kumar Raut, and then this will be followed by Madhusmita Sahu. Saroj, if my memory goes right, Saroj did his MSc in 2007 from Utkal University. He was our student, one of the brightest students. Then he went to IIT Guwahati when he did his PhD in 2000, from 2009 to 2015, working under Professor Bhishma Patel, B.K. Patel. He is also from Odisha. And then after completing his PhD, Saroj went to University of Texas at San Antonio. From 2015, he was there with Professor Zhao, C.G. Zhao. And then after that, he moved to the University of Louvain with Professor Oliver Riant. And then at the present, he is a postdoctoral associate at Ludwig Maximilian at Munich, Germany, with Professor Paul Nochel. So Saroj has a very good training in the area of organic chemistry. And I'm also happy to know that Saroj is also married to his classmate, Jyotirekha Mahanti of IIT Madras. I think I am right. Saroj was an outstanding student. He qualified NET and GATE, and also he was a JAM qualified student. He has a lot of experience in the area of organic chemistry because his training is very good at different places. I hope Saroj should come back to India and occupy a position in good institute, maybe IIT or NISER, ISER or Central University, any place. So I have not seen Saroj for the long time. With this introduction, I now invite Saroj to start his lecture.
Devasis, please.
Am I audible, sir?
We can't see
Saroj.
you. You are audible, very much audible, but we can't see you.
Yeah, you can see me?
Yes.
Saroj, can you see me?
Yes, sir. Yes, sir.
Please tell your screen name so that I can make you co-host to share the screen.
So myself, Saroj Kumar Raut. I can't.
Saroj Kumar Raut.
Yeah, I got it.
Yeah, it's fine.
Yeah, fine.
You can see my screen.
Yes. So
now you are now in Munich.
Yes, sir.
Oh, it must be very cold then, because Germany at this time there will be a lot of snow.
Yeah, definitely, sir. Yeah, it's very cold. Almost it's going minus 2 to 3 degree currently.
Yes.
What is your local time, Saroj?
It's a local time here is 8:30 in the morning.
Morning. Okay, that's good.
8:30 morning. Okay.
Yes,
okay. So here it is almost 1 o'clock, 1 p.m.
Okay, sir.
Okay. I think you are in this university, Ludwig Maximilian, Munich?
Yes, sir.
Achha. Our Professor K.C. Das was in Technical University, Munich. Professor K.C. Das For some time, he was in Technical University at Munich, Germany. I remember.
These two universities are very close by, sir, and it's hardly take 10
Oh,
minutes.
it's close by.
Yes.
Oh, okay. Okay, so Saroj, it's a pleasure on my part to see you after a long time. You please confine to the timing.
Yes,
Confine to the timing, and the timing allotted to you is you can start say 25 minutes to 30 minutes maximum.
25 minutes.
25 minutes.
Yes.
So, am I audible, and can you see my slides? And
share your slide, please. You have not yet shared it.
Okay.
Yes, now it's okay.
And thank you, sir, for your kind introduction, and so very elaborate introduction for me. And thanks for bottom of my heart, sir. And I'd like to also thank to the all the respected member of Orissa Chemical Society and the organizing committee for arranging this conference. And to everybody knows that the medicinal chemistry really relies on the basis of synthesis organic chemistry. So it is a very basic foundation of medicinal chemistry to access the molecule using organic synthesis. And so on the basis, my topic is today is about the developing new approach and to deliver this kind of synthesis. So I divide my topic into three parts. The first part is I'm talking about the strand ring in the drug molecules, so how easily to access this molecule using different approach. The next part, I'm going to speak about the enantioselective CC bond formation using organocatalysts. So basically, I'll talk about the manic reaction. The last part of my talk will be the CH functionalization, and there is a new tool for organic synthesis and how to access the molecule for basically for the CC and CO bond formation. And I'll talk about the synthesis of ester using directing approach. Next slide, please. And you see the in drug molecules, you'll find the benzene is a very common moiety, or your phenylalanine is very common. I can show two examples here, which is the very blockbuster drugs from the for Alzheimer's disease, developed by the Bristol BMS company, and other one is the Daraflate B1, and who for cardiovascular disease. If you see these two molecules are associated with the phenylalanine, but it somehow creates problems, like the problems related to the toxicity and planarity and the solubility, even more importantly, bioavailability. So there is a demand to change this phenylalanine or to with some suitable bioester. The most common bioester for the phenylalanine is bicyclo-1,1-pentane, and the reason behind is the very dihedral, all the dihedangles are all same, as well as the distance between the two conjugate atoms is quite similar for benzene as and bicyclo-1,1-pentane. I can show you that once you replace this molecule with bicyclo-1,1-pentane, particularly for the left-hand side of the molecule, you have a fluorine containing phenylalanine. If you replace with the bicyclo-1,1-pentane, there is a significant change in the physiochemical profile. For example, solubility, metabolism activity, and a lot of things. And in the right part of a molecule is a good example of planarity. And again, so if you have a to phenylalanine, you change with the bicyclo-1,1-pentane thing, and there is an improvement of profile as well as the maintain the same activity. The problem lies introduction of moiety in this molecule, and it takes a lot of steps and to synthesize. We are quite interested in this moiety because if you, I'll show in future slides how difficult to introduce the core fragment of bicyclo-1,1 moiety. It takes a lot of steps and to synthesize this molecule. Then the question is how to access this bicyclopentane moiety very easily and in a very straightforward way. There is only one way to do this one is to just direct opening of the very strain molecule, and which is known as a 1,1-propylene. And you can synthesize the 1,1-propylene from the corresponding halide with treating with organolithium and within ether -45 to 0 degree in 2 hours, you'll get the 1,1-propylene, and you can validate the concentration of the solution in ether 0.6 to 0.8 molar solution. And there is we are not the first people opening the ring. There is a very pioneer work developed by the Scripps Research Institute by Professor Phyllis Barron and my current supervisor, Professor Paul Nochel. And they developed that using the turbo-Grignard reaction, the first approach of Phyllis Barron to substitute the amination. And then subsequently, Professor Paul Nochel has described that the organomagnesium and the Grignardians can open easily, and you can do the difunctionalization. So that's the beauty of this work. And they also suggested about the alkyne as a bioisoster of this bicyclo-1,1-pentane. What is our contribution to this area is we are quite interested on the introducing the xanthate moiety on bicyclopentane. So how can we achieve that one? The first approach we did, we have synthesized the xanthate using alpha haloketone, and you can take this alpha haloketone and treat it with the corresponding xanthate, so you can achieve this transition, and a lot of steps, sometimes some of the xanthates required. And then you treat with the propylene, one very strain ring, and in presence of 20% diluted peroxide in dichloromethane and 80 degree and 8 to 10 hours, and in a cell tube, we can able to access this molecule. And further, we confirm the structure of the molecule by X-ray crystallography. And the fundamental idea behind to putting this xanthate was to access further functionalizations. The functionalizations like the hydroxy compound or this SCF3 compound, SH molecule, and olefination, and you can access variety of molecules. So I promise I'll show a couple of transformation in my future slides. And this transformation, you can rely on the mechanism from taking use our experimental evidence as well as from literature support. So what is the laureate flux usually deacylate and you give the radicals A, and which react with your compound to xanthate and give the active radical B, which is responsible and driving force for the opening the propylene ring, and it will get the intermediate C, and then it react with one molecule of xanthate and give to the intermediate D, and which is for the radical cleavage here, and you'll get the desired product, and then you'll get back the active radical, which continue the catalytic cycle. And we try to isolate any of intermediate, and it's very difficult to edit, because at the beginning it's captured the radical form, whether it's from the lauryl peroxide with the tempo, you'll able to isolate tempo ether. And so in future, we're just planning to do some computing study to calculate this one. Then the next slides, you're going to the scope of the reaction. The scope is very wide, and you can show a couple of examples here. You can see the from aromatic substituent in the presence of electron donating withdrawing group. Even if you put the heteroaromatic system, you can achieve all the BCP moiety containing xanthate molecule. And also, we're not restricted to the aromatic system, then going to aliphatic, even if quite interesting, the strain ring, the cyclopropyl, cyclobutyl, and you can even go for the ester, not restricted to ketone, and you can functional ester as well. And also sensitive functional group like nitrile, you can functionalize on that as well. And also very complex molecule, you can steroid, you can put the chloric acid in this system. And as I promised at the beginning of my talk, we are to able to give an alternative approach for the synthesis of very important the fragment of the bicyclopentane moiety in the darafluoride with the cardiovascular drug. So if you look at the original synthetic routes, it takes almost 7 steps, and it is associated with a lot of harsh condition. So what is our contribution to synthesize the basic fragment is to take the xanthate. We have a very good quantity of this one, and to just to do the cross coupling with this using the photocatalyst, and you just with collaboration of Professor Ben Elias group within UC Leuven. And we did with various screen a lot of kinds, although the yield is not that great compared to this one, but it is quite worth to just study this. And you can do the Hofmann-Bremer reaction. You can just get the amine, and which is a most ahead of one step corresponding to, you get the acid here, but we can get the amine and further do by trying to do the further function to achieve this complex molecule. And I told you it's a very potential, that is Xanthate as a very potential way to functionalize. So we taken very complex molecule, I told the proleic acid, and you can synthesize this precursor, Xanthate precursor, using the 4 steps, and you can do the Xanthate, then you can treat our condition and able to access this molecule. And then once you have this molecule, and then you can do the transformation, and very fissile group you can do transformation, which is SCF3 agent. And this is, you can do the same catalyst, and you can in chlorobenzene 4 hour, you can do transformation. So the fundamental thing is that this fluorine is very good molecule for biological compound. It's have high electronegativity. It can also affect your drug molecule. And the next part, we just, this group has a fragile one, you can cleave this one, and you can make the thiol out of this one. You take the ethylene diamine in ethanol at room temperature, you get the thiol. And we also observe some of the dimer product of the thiol, but we will able to manage a very good yield of this thiol. And then we do the in reaction with allyl glycoside, to put the sugar moiety on it. It can also very useful for the biological point of view. And you do the collaboration with Professor Elias group and with in photocatalyst. Also able to success to deliver the CC bond formation in a strain ring is quite and you able do the ethyl sulfonate, and you can use peroxide and use the 130 degree and 124, you will get able to achieve this. Although its yield is very less, because we most of the time observe the falling of Xanthate moiety and from the corresponding molecule. And this is all about the first part of my talk. We are not restricted to the only 1,1-propylene, and we are also having a very preliminary correlation with this kind of strain molecule. You can see that we can access the 4-membered strain molecule or with heteroatom containing strain molecule, and it's quietly useful in biological system. This end of my first part of the talk, so I'll go to the next part of the talk, which is about the enantioselective CC bond formation in manic reactions. So you know the manic reaction is very usual studies using the very famous organocatalyst, the L-fluorine, and you can take the aldehyde and corresponding imine, you can do the transformation. But the problem arises when you have a very system like ester. Ester is very less pronucleophile and very less electrophilic compared to the other aldehyde ketone, and then it can, it's very difficult to functionalize. So then we screen a lot of organocatalysts. Specifically, we are interested on this kind of tertiary amine containing the synchronoalkyl derivative. We screen a lot of catalysts. I'm not able to show all the catalysts here, but I am showing the only active catalyst which was represented here. You can see the complexity of this catalyst. You can fluorine and you can amide bond, urea bond, and as well as the amine. And once we treated with this one is in unsaturated ester system, and you have a methyl group here, which is responsible for the selectivity, you can say, because it's specifically organised, and it treated with the antosal imine, and you can generate beta amino ester also. So this product you get the good enantioselectivity as well as the high diastereoselectivity, and this product also in the usage of some of the very complex molecule. I can show the Taxol. You can see alpha, beta, and esters is present there. So there is an alternative ways to access this molecule using this organocatalyst. And to confirm the stereochemistry of the molecule, so we have a proposed favored mechanism. If you see this one, this molecule has the tertiary capture the proton. You have an anion interaction. And then the amide bond here is there. It can't make a hydrogen bonding to this to imine, and it can orient in such a way there is a less steric hindrance, and you can get only one side attack from the back of the side. You can get the SS product from here, and you can, that was confirmed, pretty confirmed from the X-ray crystallography. You can see from, and it was got the crystal from in a DMSO. And then the important thing is about the substrate as well as the application of the reaction. We did a lot of substrate. I was just showing a couple of substrate here. You can see there is electron donating as well as rhododendron present in the aromatic system, also as well in the tosyl group. But the application is quite interesting because we can selectively decleavage the tosyl group by putting the benzyl chloride here. You can see that in triethylamine, in DMAP, in THF, in 24 hours, you can get the benzylation here. And you selectively, you can cleave one of them from the tosyl using samarium iodide, and you can get the benzylation, which is also useful for the beta amino ester synthesis. And then you can do the reduction. Other part is also active. There ester is there. You can reduce with the standard reducing agent lithium aluminum hydride in the -70 to 0 to 7 to RT. And you can get the homoallyl alcohol with the, then you do the bromoetherification, and you can get the tetrahydrofuran moiety, which highly substituted and with high enhancer selectivity and good direction. You can imagine 99:1, even of a very highly functional molecule. This all brings me to ending of the second part of this. How can I access this molecule and selectivity using the very technique of this organocatalyst. The last part of my talk is about the CH functionalization, which is a very new tool, I can say, and emerging to last couple of in a decade, you can say. And the basic fundamental behind is why we need the CH functionalizers. The idea is to access the molecule even if you don't have any functional group. You can metallated, you can make CC bond formation even if your hydrogen, only carbon hydrogen bond. And there is there is a famous Nobel Prize got from the cross coupling. In cross coupling, the problem is that you need a functional group and free functional. You need the bromine, you need the trophlate, and boronic acid, and you can do CC bond formation. But the technology, new technology of CH functional, you don't need that one. You just not a hydrogen bond only. You can do the CC bond formation. Although it required some of the approach like distal approach or some of the like directing approach, and the advantage is that it's a quite reduced step, and for the industrial scale it can be cost effective. And so they are specifically focused about the arene system, because you can arene, you have in this particular in the phenyl system you have a ortho, meta, and para bond. So I will focus about the orthofunctionalization, but I can show that how this field has grown over to access the meta even of selectively, and access to the para position, and you could go with using the transmetal catalyst. You can show very beautiful work by the Dhenkanal Yu. He designed the template like that. You can just get a linear coordination to the metal catalyst, and you can selectively cleave the meta bond without touching the ortho and para. And a similar, the very famous work by Dept Moidip from IIT Bombay, and he told that this molecule can access to the para positions. And the power of this technology has gone such far that you can access all the carbon hydrogen bond, and you can do the sequential CH functionalization to access very complex molecule that I did. So what we did during my PhD time to do this CH functionalization, we tried to do CC bond formation in alkene and alkyne. So if you look at we have seen the literature, there is a very much tedious catalyst required to do the CC bond formation. Rhodium, lithium is quite expensive. So we try to replicate using the very less expensive catalyst in the copper, in principle peroxide, and we want to do the CC bond formation. But unfortunately, we did not get any CC bond product, rather than got the benzoxy product. So it is quite disappointing from beginning result. But when you look at carefully the product, which is quite happy, because from the mechanicity point of view, using CH functionalization, you will lose one of the carbon moiety from your parent alkene. So we're trying to evaluate, so what is the going on this one? Then we did lot of control experiment and observe some of the intermediates forming in the reaction. The first intermediate we observe is a glyoxal and the aldehyde, and corresponding to the benzoxy radical, which is responsive for the benzoxylation. And so then we try to evaluate how it is forming the alkene to glyoxal, and then we did control experiments with epoxide as well as the diol, but we not got any product in our condition. So then to try to evaluate the second step to glyoxal to aldehyde, then we did an experiment with palladium chloride and polymeridium test, where you can see that you have a strip containing yellow solution. After the reaction, it turns to pale blue, and it is just evaluate you have a reaction and evolution of carbon monoxide and extrusion of carbon monoxide. Then you try to this aldehyde capture with corresponding tempo. You are able to capture this tempo ester, and followed by the radical of your benzoxy radical. Then if you look at the catalyst, once you have benzoxy radical, then other part of the catalyst cycle, the copper is going to the 2-phenylpyridine. You'll get the complexation here, and then the oxidative addition happens. Then you'll get the copper 3 intermediate, and then you finally deduct which you get the benphenyl benzoate. And we have very good substrate score for this reaction, and we get to use the very 2-phenylpyridine, and you get the benzoxylation of different alkenes and alkynes in the molecule. This end about my today's presentation. So I hope I able to convince the people and able to put the bicyclopentane moiety efficiently in very simple to complex system using very strained molecule in a straightforward manner, and which has, I hope it is a very potential application for this one. The next part of I discuss about the enantioselective CC bond formation in the vanillin reaction using a very organocatalyst. The last part about the CH functionalization. So I able to all the because of time I just to talk about the esterification, and but we have a lot of results about the arylation as well as the construction of various using sp2 and as well as sp3 CH bonds. And I'd like to thank a couple of members, especially my thesis supervisor, Professor Vismankant. We had a carried CH functionalization, and the work of organocatalysts carried in the USA. About Professor Zhao, I learned about the organocatalysts, how to handle this one, the low temperature, and the last part of the propellant chemistry is in the done in the Professor Oliver Lant lab, and about. And this all I thanks to all the co-workers who contributed in my work. And thank you very much. And this is the current group of my you can see the pictures. There is a quite traditional pictures. It is known as very famous in Munich. It's Oktoberfest, and it's due to the today current COVID-19 pandemic. It's not happening, but it's a very popular. You can see all our lab members are arranging the dress. And thank you once again for Orissa Chemical Society for invitation, and especially for Dr. Pridhar Mahapatra, who given the invitations, and also my friend Vigyan, who coordinated this one, and last not least my teacher Professor Satyanjana, who has given a wonderful introduction of me. Thank you, sir, very much. I'm happy to answer all of your questions if anything. Thank you very much.
Professor Jana, please.
Saroj, may I ask you one question?
Yes, sure, sir.
Acha. So you have taken a strained ring in the first part of your lecture. You have taken a strained ring as a spacer.
Yes,
spacer. Acha. Why have you gone for a 4-membered one, bicyclo? But why not adamantane? To me, it appears adamantane is a caged molecule and lot of space is available. So what is the reason for taking a bicyclic 4-membered ring?
Yes, sir. You're right, sir. Absolutely right.
Instead of taking adamantane.
Yes, sir. You are absolutely right. The adamantanes, we have literature evidence for this one, because people, other group in the US, they're working on adamantane, putting the xanthate on that one. So that is they have been working on that one. And other things, the bicyclopentane has a very biological relevance for as a bioassistor. So we are mainly focusing on the mainly focusing on the bioassistor of phenyl ring, so which have a potential way to synthesize this molecule. So we particular this region to bioisoster synthesis, we have taken this bicyclo 1,1, particularly 1,1-propylene.
Acha, okay. Another small question is that you see in the last part of your lecture in CH functionalization, you have compared a Heck reaction with Fujiwara Moritani reaction. Yes.
Yes, sir.
But you see, if you take Heck reaction, you have one advantage, scene addition and scene elimination.
Yes,
but
sir.
what about this Fujiwara Moritani? Is there such a selectivity or what is
Yeah,
the
the selectivity, the selectivities are come from the ligand you are using, or particularly the ligand control, because the CH functionalise also relies on the ligand, what kind of ligand you are using. It can control your selectivity of this one. When you are going to the reductive elimination, that can control it. The specific role of the ligand is very important, sir, in CH functionalization.
Yes, I understand, because you see, if you have a triplet and a chloride, normally the triplet overtakes the chloride in cross coupling.
Yes, sir.
But if you change the ligand to para tertiary butyl, try para tertiary butyl, very hindered ligand, then the reverse is true. That means chloride overtakes triplet.
No, yes,
Anyway,
yes.
Okay. So,
Right. But the CH functions
thank
has
you,
been.
Saros.
Yes, sir.
So anyway, so as you said, the ligand control is important.
Yeah.
Sometimes if you want to eliminate triplet, you can choose a ligand, unhindered ligand. And if you want to overtake chloride plate, you have to choose bulky ligands attached to puspin.
Yeah.
Anyway, so this is a very interesting lecture. And is there any other question from anybody else? Sasadrao, any other question anybody has asked?
Let us thank him and move over, because we are running short of time.
Okay.
Just with your permission, one small point. This is time for panel discussion, and probably Professor Behera might be waiting for us. From my side, I apologize that there will be a delay of around another 25 minutes for the panel discussion to start. So if Professor Behera is listening, sir, kindly bear with us for another 25 minutes. The last lecture, which will be finished, and then we shall have the panel discussion. Professor Jena, please start the next.
Okay. Okay. So the next speaker is Madhusmita Sahu. Madhusmita Sahu. Madhusmita, can you hear me?
Yes, sir, I can hear you.
Acha. So it is also my pleasure to introduce Madhusmita Sahu, who was also our student from Utkal University. Madhusmita was a gold medalist in Ravenshaw College in honors, and she passed from Utkal University, and then she qualified the BRC. Presently, she is a scientist at IGCAR Kalpakam. She did her PhD from HBNI in 2018. Madhusmita is also NET and GATE qualified. She was a very prominent student and excellent among the girls. She is presently a scientific officer at the level E at Indira Gandhi Center for Atomic Research at Kalpakam. And I know she works in the material science group. So we'll be very happy to hear a lecture from Madhusmita in the area of material chemistry. So with this, I invite Madhusmita Sahu to start the lecture.
Hello.
Yes.
Sir, can you hear?
Madhusmita, madam.
It is visible. Your screen is visible.
But we can't see her. At least we should see her once.
Yeah.
Once
Sir, how do I?
Okay.
Yeah.
Yes.
Yeah.
Go ahead.
Yeah, good afternoon, sir. And actually, I was the kind of fangirl of Satyavan sir in my MSc days. And anyway, I wanted to pursue organic chemistry, but the job took over. So somehow.
Okay, okay.
So it's actually I wanted to see him. Means it would have been really good to see him physically, but could never got the opportunity. And in addition, it's means because of COVID, I'm just able to see him on the screen. But it's a very happy occasion. So
Okay, thank you.
and
Thank you, Madhusmita.
yeah. Sir, maybe I will means just complete the talk and then we can discuss about the things a little bit more. So I will first means I just went through the means have been listening to the previous talks. They are very good and more informed. I would like to, I have kept it at very basic level because I was told that BSc and MSc students should be means the target audience is BSc and MSc students. So as you know, I'm working in Department of Atomic Energy, and we have a national facility at RRK at Indore. That is only one synchrotron which we have. So now that the Prime Minister is talking about Atmanirbhar Bharat, this is a very flagship program, and I don't know how many researchers are using that synchrotron facility right now. But I would just brief a little bit of that, means use one technique and explain you in detail how you can utilize and means utilize the national facility, and along with that you can continue your research. So the talk my talk will be based on means it's X-ray absorption spectroscopy and how we use it to delineate the location of a particular atom, and you can actually utilize it for any system, be it liquid, solid, or means organic system, inorganic system. It's a very powerful technique. So the first I will explain the motivation for the EXA study, and then the basics of it, and then the brief outline of how you go about doing the analysis, and then the results and discussion with respect to a particular molecule. Particular solid, actually it's not a molecule. I'm working in materials means thin films now. So let's move over. So the material that I had chosen is simple TiO2. TiO2 is known as a photocatalytic material, and the research is being done for over last 20 to 30 minutes, 30 years. So it has just 3 pages: anatase, rutile, and brucite. Anatase is a metastable phase, and its space group is I41 by AMD. All of us chemists, we read that point group symmetry, but when you move to material chemistry, good that you bring it up little bit more and read about how that molecular level symmetry gets translated to solids. So the space group describes basically that, and it has various applications. I will not get into the applications. I will only cover the basic X-ray absorption spectroscopy and how you utilize it. So and the synthesis was done by a spray pyrolysis system, where I have taken a organometallic molecule, titanium oxyacetyl acetonate, and has been deposited by using this is a heater. Just nebulize it, and then vary the parameters like height and other things, and then your film will be deposited. This is the XRD pattern, and you just confirm the phase of it, and it was a phase pure anatase. Phase purity is important when you go for analysis of a means basic for basic characteristics like exapts. If you have more than one phase, then you'll have difficulty while fitting. So that phase purity has been confirmed. Now the thing is that I have doped nitrogen by taking hexamine. So the point is, how do I confirm whether nitrogen has been doped or not? So simple, do a XPS analysis, and then you get to know whether your nitrogen is doped or not. I get that the nitrogen is doped, and these two peaks are for interstitial nitrogen, where the nitrogen doesn't sit at a crystal lattice point, rather it sits means at some at point which is not a lattice point, and then this is a substitutional nitrogen. Substitutional nitrogen means it is actually, it will replace the means crystallographic lattice point. So then you calculate its concentration by using this formula, and then but the point is, XPS is a surface analytical tool. So the problem is, how do you know whether it has got whether it has actually gone to substitutional or interstitial. Why is it important? Because if it is substitutional, then there will be intermediate states which will be formed just above the valence band. However, if it is interstitial, this gap will be more, and accordingly your photocatalytic properties will vary, and so will other electrical properties also will vary. So this is how the titanium dioxide looks at a local level. This is a titanium oxide octahedron, and when you introduce a nitrogen, it can go to the interstitial or a substitutional level. So you have to, my aim is to basically find out whether it is substitutional or interstitial, and how does it sit, at what bond length, and what coordination number. For that, before that, we'll have to find out whether it has affected any band gap change or not. So for that, Tauk's plot was done, and then I found out that the band gap is around 3.2 to 3.18. Apart from that, there are some intermediate states which are at 2.293 or below 3.2. So this will basically make sure that 3IO, which is previously absorbing only UV light, now it can absorb also visible light. This is a significant part of catalytic industry, that whether you can make a material from UV active to visible light active, because the basic part of our sunlight is our visible light. Solar UV light constitutes only 5%. So the entire solar cell industry, or the power to utilize your solar energy depends on whether your material is active to visible light or not. So this is a part of that work, and it has got published in SES Applied Materials and Interfaces. But right now my concern is, how do I know where is the nitrogen present? So this is the X-ray absorption studies is basically done in a synchrotron, and our synchrotron is a national facility of 2.5 GeV electron ring, and it is present in Indore. I wish more researchers use the facility. So what is X-ray absorption studies? It explains how X-ray is absorbed by an atom at energies near and above the core level binding energy of the atom. So what we do, and the spectra is basically the X-ray absorption probability versus energy. So a typical X-ray absorption spectra will look like this, and this is your edge. Edge means this is when the absorption takes place. This region is rich in chemistry. What does it say? It says about the electronic transitions. All of us who have studied at Utkal University have studied group theory. So this is our favorite. This would be our favorite portion. So thing is that this will basically tell you what are the electronic transitions. If you are somebody has reported in the literature, then you report it. Else you do a molecular orbital diagram, proper theory calculation, and then find out what particular energy it lies, and then you say that this particular peak is for this electronic transition. And this particular region is also known as JANS, X-ray absorption near a spectroscopy. The interesting part is this is extended X-ray absorption fine structure. So the fine structure, I'll go to little bit of mathematics here. How do you what does it exactly tell me? X-abs will give me basically the coordination number and the radial distance. At a basic level, at some point of time you will know that if the bond length varies, then your magnetic properties will vary, then your the amount of energy required to take a particular element out of it, crystal lattice will vary. There can be many applications, but so how does this X-abs portion tell us the coordination number and the radial distance? So what we will do, we'll find out what exactly X-abs does. So what happens in X-abs is, this is your core atom. So an X-ray photon will and the X-ray interacts with matter in two ways. Either it scatters or it absorbs. Right now we are considering the absorption. So what happens is that in the regime of X-ray energy, as electromagnetic radiation can interact with matter in various ways, and the electromagnetic radiation will also have its own spectrum, wavelength range. But in the X-ray regime, primarily it interacts with the matter as through a photoelectric effect. So what will happen is, once you give this X-ray to the to your material, and depending on what energy you are giving, either your K cell or L cell or M cell, that one electron will be knocked out. So that is basically your photoelectron. So that photoelectron will travel to the nearest neighbor and then get reflected back. So this is like a Young's double slit experiment. So what happens is that when it gets reflected back by the nearest neighbor electron cloud, you will have an electromagnetic wave being reflected back. So that can undergo a constructive or destructive interference. That constructive and destructive interference will ride over this region as a sinusoidal wave. So you analyze that sinusoidal wave and find out, since it is getting reflected back from the nearest neighbor, so how many such nearest neighbor atoms are there, and then at what distance. That information will be contained in that region. So you analyze that portion and find out what is exactly your coordination number and what is exactly your radial distance. So so this is a typical experimental setup. We'll come to the exap's part a little bit later. So you have an X-ray source, you have monochromator, slits, and then your sample. Then this is a simple absorption spectra. Means I have not shown the picture. Maybe you might have appreciated the beamline more, but this is a simple schematic how the experiment is done. And you either get the data by the fluorescence intensity, or by transmission, or by electron. These are simply different modes of data acquisition. So I will not get into details of it. You choose which one you need depending on your sample quality and the sample you have at hand. So this is it. This is the spectra that I showed previously. So this is my pre-edge peak. Pre-edge peak, how is it reached? Because if you have a tetrahedral system, you will have only a single peak. However, if your symmetry gets varied from tetrahedral to octahedral or something like D4H or C4B, then once your system lacks center of symmetry, this peak will get split. And then you analyze it. So as you can see, I have 3 peaks here. So that means this 1s to 3D transition will happen. And when my system is actually TiO6 octahedron, but because of the distortion, my system lacks a center of inversion. So then what happens is, I found that, so since TiO2 is a distorted TiO6 octahedron, I found that it has 3 peaks corresponding to different transitions, which has been marked here. This is basically your molecular orbital diagram, and it's a Herculean task actually to create a molecular orbital diagram from the core level to the end. And initially when we study oxygen, nitrogen, we feel that okay, simply draw the lines and then you are done with the molecular orbital diagram. But it is means I am banging my head for last 1 year to get a simple molecular orbital diagram calculated for SNO2. So we as students during BSc and MSc days, we really didn't appreciate that how much effort that goes into the calculation part. But finally, I hope I'll get something on SNO2, which I'm working on a different project. So thing is that this is your molecular orbital diagram, and which electron is exactly getting excited to which one. What you do is you simply allow your selection rule to be allowed, and then find out at what energy it is coming. So do that a little bit of back calculation is there, but this is what the technique overall tells you. So how does this X-ray absorption fine structure work? So this is basically my absorption coefficient. So this is a this is the function, and then this is the absorption coefficient for the measured absorption coefficient. This is your smooth bare atom background, if there is no other atom present, then what is your absorption coefficient? This is a theoretically calculated value. You cannot get it experimentally, but you can calculate it theoretically by isolating all other atoms and then taking care of all the screening effects. And then you have this chi E, and then if you change this energy to the wave number k, you will get this equation, and finally you will have this equation, which is a sinusoidal function. And the reason of giving this thing is that how this sinusoidal function is riding over that final edge portion after the edge. So and in this equation you can see that we have n is the number of nearest neighbors that is present in the atom that you are looking at, and r is your radial distance, and sigma square is your Debye-Waller factor. So thing is that development, how do we develop that X-ups equation? Everybody might have read that quantum mechanical treatment of that ground state and excited state. You have a ground state and excited state, and what are your components in the ground state? You have an initial state, which an X-ray, a core electron, and no photoelectron. And then there is since core electron is tightly bound, initial state will not be altered by the neighboring atom. However, when you go to the final state will have a photoelectron, and the function will get altered by the nearest neighbor. So you simply calculate this function, and then you'll have the square term and the complex conjugate, and you'll develop an equation like this. It is a very simple equation. You can just work out in your means a copy. Maybe a blackboard would have been better, but we have to deal with this. So then what happens is that X-ray absorption fine structure is basically due to the oscillation at the observing atom caused by the scattering of the neighboring atom. So what are the three physical phenomena that is happening? One is that the photoelectron wave travels as a spherical wave, like the normal Young's double slit experiment, and then it travels to the nearest neighbor R, and then scatters back as a spherical wave. So you write a of spherical wave equation, and then combine all these three terms, and you will get this. So, and this is for one atom. And what we are measuring in X-ray absorption spectroscopy is the collective average of all such atoms. So what happens is that this is again that equation, how it gets developed. I'll just browse through because just 20 minutes is given. So thing is that this is basically the heart of the equation, and you find that there are some three parameters, n, r, and sigma square. I will tell why it is important later. So this is a typical X-ray absorption means spectra that you get. How do you handle data? So the thing is that for handling the data, you have to have people have developed already software. So we use two softwares, Athena and Artemis. And what happens is that in Athena, you treat the data to clear the initial noise, and then check for any self-absorption, fit the pre-edge and the post-edge background correction, and then you will get the data in KK format. I am explaining this particularly if anybody is doing particularly pursuing this kind of work, or in BSc or MSc, and they can have a feel about how the data is handled. So, and then give the suitable crystallographic input, and then generate the scattering paths, optimize these parameters, and there will be a factor, R factor, which you minimize, and then get the information. So this is how typically the data is handled. This is a pre-edge region, means this region, and normalization region is your post-edge region. This is a cubic spline function, and this is a straight linear function. Fit it, and then derive your chi-r value, radial distribution function. How many people are aware of the radial distribution function at this stage? So, but this is your basically first coordination sphere, and then and we do not get more than two coordination sphere in this kind of experimental setup. 2 minutes.
Yes.
Okay. So I will finish, sir. Maybe one more minute. So basically you do this normalization process. Then I will skip over how you take the crystallographic input, and then you want to replace one atom, replace. This has more to it. Since I have only 2 minutes, I am just scraping through. So, and then this is a typical how you handle that. A lot of information goes into this, like your crystallographic information, where does your atom sits, and which particular atom you want to replace, and then take all the information and then fit it and find out. This is a typical means fit. How does it look? From this, the goodness of the fit is measured by this statistical parameter, and this R value has to be less than 0.05. And then you have all this is the information. This is the information that we all need. These are the paths that I took to fit, and then bond length, coordination number, and your this is just means information for the reviewer. So the thing is that I have got that the titan, I have taken a separate titanium nitride path to fit it, and have found out that this is a interstitial atom, because had it been substitutional, then I would have taken this oxygen, replaced this oxygen with the nitrogen. Pretty basic. So thing is that that is how you means all that I want to drive home the point is you exactly know where your atom is sitting. You pinpoint the position of the atom and then what is the bond length and whatever changes with respect to bond length and the symmetry, you get that information. Like if your system is changing from C4V to D4H, so or suppose D4H to octahedron, so everything you get this information from this one particular spectra, and then you take it to the physical information, like whether your magnetic property is changing, whether your band gap is changing. Every application you means everything that is related to bond length, coordination number, and the local symmetry, you get all sorts of information from this. One application that I would like to highlight from this particular technique is that we have a Ayurvedic medicine Rasa Sindura. So that is a medicine which is based on mercury. It has been debated for pretty long time that how come mercury is means mercury is toxic, all of us know, but then how does that medicine work? Then one of our scientists, she took the material and then studied its oxidation state and its bond length and everything, and proved that the mercury, the oxidation state of mercury in that particular medicine is non-toxic, because it was staying in probably zero oxidation state or something like that. So it has huge potential, huge. Just take anything, any metal, any atom, and you want to study what exactly is its basic properties. Use the technique, be done with it. Little bit involved, but this is what we have in our own country. Go have Indian food and do the experiments. So the thing that is the primary focal point of my information now. So this is like this is what I have calculated, and I have found out that my values were little bit better than the previously reported values, and then this got published in JPCC. So the location of nitrogen, and this is just one paper. I thought I will keep it simple, but because I was told that this will go for 40 minutes only. So yesterday I came to know that it is for 20 minutes. So anyway, the location of nitrogen was found to be interstitial. Presence of free peak confirmed the distortion in octahedron. So anybody who is interested in the local symmetric group theory, this is your area. You can really sign. And this is an area where hardly 10 to 15 fellows in India are working, and probably all of them are not pursuing. They are doing it part time. Like somebody has a metal means metal center for some organometallic compound, they will do it. But only there is a group in BRC. There are some 4 or 5 scientists, and I am in sitting in IGCAR. I am one, because we have permanent jobs, we are pursuing. So anybody who wants to pursue, this is a developing field and has developed only for just last 20 to 25 years. So anybody is in material science and inorganic chemistry or organometallic wants to pursue, I know Janessa would not be happy, but I hope I have made him proud in MSc race. But anyone who cannot get means who cannot get into organic chemistry but is interested to pursue, this is a field where they can pursue, and people are getting pretty good jobs. Thank you. Thank you. And I always find it pretty difficult to thank you each and every person, because I'm too obliged for every little contribution that I have got from all my circles, because they have been really sincere ones. So I thank you all from the bottom of my heart. Thank you.
Okay, I have just one question. You talked about that mercury compound, which is Sila Sindur. So similarly, there is
Rasa Sindura.
Rasa Sindura. Okay, it has another name, Sila Sindur.
Okay.
And there is Swarna Bhasma and
yes.
Are these things been studied?
Yeah, actually one of our senior scientists took it up, but she didn't pursue it. She just proved one molecule of Rasa Sindura. So that was even pretty interesting to me also, but it can be done. Right now, I will pursue it maybe after 2-3 years.
There are a lot of questions regarding the medical ethics that is followed in
Ayurvedic. Yes, we can actually we are raising this issue to the higher ups, but see just 4 to 5 persons are following this topic, so it's very difficult to cover all the medicinal properties of all the Ayurvedic medicines, but it's a developing area. Yes, I hope in next 10-15 years we'll be able to establish. At least I myself will take 2-3 molecules in my next 3-4 years.
Please do it. Please do it. It is interesting. Yes.
Yeah,
Okay.
yeah.
Very nice presentation by Madhusmita. Very nice. Though I little bit understood that MO diagram construction is very difficult, but I thought that it was very easy because I only studied oxygen, nitrogen, and carbon dioxide. That's all.
Yes, sir. Sir, I am banging my head for last 1 year, and that theoretical calculation is not everybody's job. A physicist or a chemist who is working in theoretical calculation, it's a very involved thing. Means I can't describe, because even this technique to even just to fit, it took me nearly 1 year, thorough 24/7 to start fitting this spectra. So that is why people do not pursue it. Only people who have a like settled life, permanent job, that kind of people. But anyway, I'm still propagating it. Some university students I have trained, so hopefully they will pursue it. And if
Okay,
anybody from Odisha are interested to learn, and I'm always available. Means to teach it in more details and let them do some more work if anybody is doing. I'm 100% available to collaborate and teach and bring up the next generation.
Okay, thank you, Madhusmita, for your nice lecture. And please convey my good wishes to your husband, Lakshmi.
Yes,
He
sir.
was my favorite student because he pursued organic chemistry.
Yeah,
He did
sir, I hope
PhD
I would have been
from
your favorite
Santosh
student.
Bharpure. No, same thing. Doesn't matter.
Okay.
And then I met him in IIC Bangalore when he was with Professor Prasad.
Yes,
I think I met him last time.
Yes, sir. I know,
Okay.
I know.
So with this, let us thank the speaker, Madhusmita, for the excellent talk. Now it is over to the president, Dr. Samal.
Dr. Mahanti, please take over.
Thank you, Satyavan sir, for presiding over the session and nicely handling the session. And I also thank both the speaker of the session. We are running late of time. So now it's time for the panel discussion. So
At the outset, I would like to apologize for the delay. Can we see chairperson Professor Gopabandhu Behra? Professor Behra? Sir, asile ki? And can you see the panelists?
No, that is.
Smruti Madam is there? And
Madam,
Professor Delekar?
Yes, I am there.
Okay.
Madam,
Yes, I can see. Okay.
Yes, sir. I am.
Sagar, Professor Delekar is also.
Yes.
Yeah, I am also present.
Yes, thank you. And Professor Swai is here. And then
Namaskar.
Namaskar.
Paritos, Professor Paritos Mahanti is also there.
Where is Paritos? Okay. So Nigam sir, he is busy in Bhubaneswar. Okay, Paritos is there. Now Gopo sir can yeah, that is better. Can you sir Gopo sir ଶୁଣି ପାରୁଛନ୍ତି କି ତାଙ୍କର କୌଣସି ନାଁ ତ ଦେଖାଯାଉନି ସାର୍ ମୁଁ କହିଥିଲି ଟିକେ ଲେଟ୍ ଲଞ୍ଚ ଆଉଟ ଚାଲିଗଲା ତ anyway so maybe let's try
Gopo sir ନାହାନ୍ତି
ତାଙ୍କର ୟୁଜର ନେମ୍ କଣ ଜାଣିଛ କି ୟୁଜର ନେମ୍ କଣ ଥିଲା okay if he's not there can we have is Dr. Mishra, Professor Mishra there? Professor Ashok Mishra, can we Professor Ashok Mishra?
Panel discussion over.
Now okay, if we do not have both the panelists, I would like to take over, and the reason for why we have a panel discussion is this. The Orissa Chemical Society has organized this particular webinar under OCS Extended Lecture Series. We did this for the specific reason. Professor Mishra is here.
I'm here.
Okay, so Professor Misra, you are a panelist for tomorrow, and today the chairperson for tomorrow, and we want for today it was Professor Gopubandhu Behera, but
Okay, I'll be there.
we do not see him. So could you please chair this session and kindly continue this?
No, if I chair, what is the topic to be discussed?
This is to I'm explaining that thing. Like we are doing it for the first time, and the reason behind this is that how to continue this kind of event, whether in-person meetings or webinars, so that we, instead of having just the regional and annual conference of OCS, we have many more such events in different pockets of the state, like Ravenshaw University, North Orissa University, Burla and Palikot, like that. So that each locality, the undergraduate and postgraduate students get a feel of research and they be influenced. So the panelists are to be asked to give their opinion, candid opinion, in what way we can improve upon this, or whether this kind of seminars are necessary or important or beneficial or not. If there are ways to improve upon it, that is the things to be discussed.
I just need to know the name of other panelists. Paritosh is there.
Yes, sir.
Asmita and Sagar Delekar.
Professor Sagar Delkar from Shivaji University is there. Professor Smriti Das of Ravenshaw University.
Oh, okay.
Professor S.K. Swami, BSSB University are there.
Okay, these people, okay.
So totally we have, including me, we are 6, is it? How many?
Total 8, but 2 are absent. I think Professor Nigamananda Das is absent and Professor Ratan Kumar, they are absent.
Naran Pradhan is also absent.
Narayan Pradhan is also absent. So we are 5. We are now 5, including the chair, 5. Right? Dr. Behra is there, Ajay Behra?
No, it's Professor B.K. Mishra. Anyway.
So kindly take over, Professor Misra. Over to Professor Misra.
Yeah. So, so basically, what I understood is how to make chemistry more accessible to essentially at the students level, I suppose, students and the researcher level at various institutions in Orissa, and what could be the best approach towards it under the constraints of Orissa Chemical Society. So for this, I think the best thing is to start with Smriti Prabha, madam. Is it okay, madam? Because you are.
Namaste, sir.
Yeah. Okay. So you have been in colleges, you have now in university, so I think you understand the system the best so far.
Right, sir. Yeah. Right, sir. Because I was in college, so I know that in college because Orissa Chemical Society is mostly based on colleges. The scope of research and scope of this doing something better for the society and for science is very, very difficult, because the scope is very less there. Only nowadays 7 hours has been fixed for the college teachers, but if there is no scope for doing some research, then what is the meaning of having 7 hours to be present in the university or college? So obviously in university we are getting some scope so that there is no issue, but for colleges it is very, very difficult. I hope the colleagues from other colleges in Odisha must accept that the scope of research and development is very less there. So if Odisha Chemical Society is attempting to do something in this regard, and if you can hear some work which has been done internationally and nationally, they may inspire the young students, young teachers to do something, to do some projects, to do some work and some internship programs, so that there can be some development in the research field.
A specific question now. So let us say Odisha Chemical Society is to be used for reaching out to colleges where the facilities are not there and accessibility is not there. So what role could Odisha Chemical Society play? One thing is sensitization, which is done, physical meetings are always good, but physical meetings are also difficult. now that this pandemic has brought in the online mode of interaction, which appears to be very successful. For example, today's Zoom meeting has been absolutely good, successful. I wasn't expecting this to hold on with so many videos, so many people keeping themselves on. It worked remarkably well. So can this kind of opportunities be harnessed at small level? And probably the answer is yes always. But then how to go about it is the question. Can something be thought about it so that?
That is the main problem, sir. Sir, Orissa Chemical Society can sensitize, but we must sensitize to have some projects, some funding, so that in colleges, with the help of this funding, we can do something. Only learning and knowing what is happening and keeping our eyes and ears open, what is said always by my teachers, that always keep your eyes and ears open. That will help you to know something, what is happening. But I think funding is essential for doing some research. It may be at any place. So I know as per the Orissa Chemical Society cannot provide funding, but they can inspire. Through this, we can get the information about different projects which can be applied, which can be possible to get in different government institutions, so that we can pursue our research work in college levels.
Thank you, madam. So maybe any other comments you would like to have? I think I will.
Maybe, I mean, other panels, one by one.
Other panels. So after then that, I'll go to Dr. Sagar. Could you reflect on this?
Professor Sagar.
Yes, sir. Yeah. Hello, sir.
Hello.
Yeah, great to see you, sir. Thank
Yeah.
you.
Hello, sir.
Yes. Hello. Hello. So
And
there
how
is
do I see? Maybe I have to go to gallery mode or something. Let me see. Yeah. Now I can see.
Okay, sir.
Yeah. I understand that maybe you are not from Orissa, right?
Right.
Yeah, I'm from Maharashtra.
So maybe you can have a outside view of what we are discussing and what we have. See, the research infrastructure, as usual, in the state is not very good for chemistry subjects anyway. So generally, under this, how do we enthuse our students to get excited about chemistry in particular and science in general, and how to keep them engaged is a question. And let us say at the grassroots level, can some small research be done which should be meaningful? That is another question. And towards that, what role this society can play?
Hello, sir.
Yes.
Yeah, okay. Yeah, okay. You have asked the 2-3 questions to me. Okay, in connection to the how one can make the chemistry easily accessible to the students and the society. In connection to that, hello.
Yeah, please go ahead.
In connection to that, the same. Already we know that chemistry is one of the important subject in science, and in connection to the science, we know that along with the theoretical part, if we are focusing more aspect on the practical approach, then definitely along with the theoretical knowledge, the student we have we are getting the students will getting the practical approach that will helpful to understand the chemistry in thorough manner. In connection to the chemistry with society in general, if you are going to see the status of India in science and technology in comparison to the globe, actually there are various the parameters. One is that how many publications we are publishing globally. Second is that how many researcher in India. And then in connection to R&D expenditure, which is spending on research. As consider if you are going to see all these parameters, number of publications, based on that, India is at the 14th rank. In case of number of researchers, we are at the 27th rank. In case of R&D expenditure, we are nearly expending around 0.68% with respect to GDP. So if you're going to see all these parameters, and if you're going to compare all these parameters with the developed country like USA and the South Korea and Canada, Australia, so though we are lagging, but anyway, the budding scientists and the scientists working at the reputed institutes are doing well. We are trying our level best. But anyway, our regular or continuous efforts are very important, so that each and every science subject, like chemistry or physics or other also, which would be useful, or their research endeavors which would be useful for the society.
Thank you. Thank you,
Can I, Professor Misra, with your permission, kind permission, please?
Please, Professor.
Professor Sagar Dhelkar is observing from outside the performance of our state.
Yeah.
My question to him is about his state. You might be having, like us, several postgraduate centers, and not all postgraduate centers are similarly or equally funded. So in the problem is that if say in Utkal University or in NIT Rourkela or in Ravenshaw University some good research is going on, similar research is not possible in Keunjhar College or Bhadrak College, where there is post-graduation but facilities are not there. So is it a similar kind of situation in your state too?
Yeah, the same situation in Maharashtra also. If you are going to see, if you are going to see the last 4 to 5 years scenario, though I am one of the faculty in State Public University, we have also opened the various PG centers at the different colleges. And though we have opened the different PG centers, and at the same time we also given the guides to the many teachers working at the UG centers, but at the end they are giving the PG degrees, but the quality of the whatever the students who are getting that degree, along with that the research which is going at their centers, somewhat they are lagging in terms of facilities, then funding. Along with that, there is usually the burden from the management. But anyway, this situation in Maharashtra is somewhat like the other part of the India. Like we are visiting to different states like Karnataka, then Andhra. The situation is somewhat same. But anyway, we have huge youngsters throughout India. But the government should take the initiative for giving the more fund, not only fund. There should be increasing the facilities, and if the funding and facilities are given to the institute like UG or the colleges, then definitely we are going to enhance or uplift over the research endeavors.
Thank you, Professor Sagar.
Thank you.
Professor Swaik, for the same 3 questions, what would be your Hello?
Yes, sir. Sir.
Yeah.
I think
we have
yes, go ahead.
Sir, we have 2 issues. One issue, first issue by predicted by Professor Smriti Prabha Madam, that how to start the research at the college level, mostly at the, you can tell, the grassroots level. Another issue is made by Professor Sagar, that publication, number of publication, quality of publication, citation, I think it is different level, and the level, the suggestion predicted by Smriti Prabha Madam is different. That Professor Sagar told all these are the blood pressure. That means number of paper, number of citation, quality, impact factor, all these are, I can tell it's a kind of blood pressure. And for to start the research, exactly, also it is many things in my mind. When I was even the secretary OCS, this was my suggestion to start some clusters in the Odisha. I can suggest my teacher, the now president, Sasdar sir, to make a cluster in to throughout the Odisha and organize small sensitize. That means how to write the project, how to bring the money, how to set up lab. Because UGC is there, CSI are there, DST there. Many of the teachers, many of the college teachers are PhD, but they do not know how to bring the money, how to write the project. Then by which that they can make a small lab. Nowadays, you know, the cost of chemical glassware and depending on the principal for bringing small equipments and even glassware chemicals is difficult. If you have a small amount of money also you can establish. That is the main motto of the Odisha Chemical Society, that if we will sensitize the college teachers, they having at least honors. That means honor student nowadays, I guess there is a project work for the honor students. They can take few good students from the honors level and motivate them to work in their lab. And this is my suggestion, Mr. Sir, that if you from the panel discussion, at least something can be recorded to make a few clusters in Odisha by taking the honors colleges at least. Then we can sensitize the teachers to write some projects to different funding agency. This is thing. And the second thing that BOS we should suggest. Sir, am I audible, sir?
Yes, yes, go ahead. Listen, loud and clear.
Yes. Sir, in that we can suggest different board of study that how to modify the syllabus. Better to have a unitary syllabus that to include the applied, because nowadays the honor syllabus and the PG syllabus and a lot of difference is there. When you are teaching at the PG stage, the honors level teaching and the PG level teaching, it completely, I cannot tell complete different, but somehow it is not recapping where they are stopped and where it is start. There is some gap. Any subject, where is suppose coordination chemistry, where they stop and where they start at the PG level. That may be sometimes it is a gap, sometimes it's overlapping. That is why we cannot do the board of study, but we can suggest all of our members at the members of the board of study of different autonomous college and university. Accordingly, I think we can make that syllabus accordingly. Sir, thank you, sir.
May I just briefly respond to Professor Swain's remarks? I would like to go back to about 3 decades from now. In 1990s, in 1980s, I was in a very small college, Vodrok College. And at that time, we were doing research, not only myself, several did research, got a PhD degree there. We had very good publications in international journals in US and UK. Now, the reason that why such centers or such places have decayed over a period of time is not that talented people are not there. The reason is that the number of such people have significantly gone down. We were 16 people, so I had the freedom to do some research after my teaching. Now there are 2 people. What they will do? The administrative work, the admission work, the examination work, they are so huge that they just can't think of research. It's a question of simple manpower problem. Even if you have the talent, you have the inclination, you want to put in hard effort, 1 or 2 people, it is just ridiculous. GM College,
You mean faculty, isn't it? 2 people means the faculty.
Kalikot College, 1 person, postgraduate center, BSc honors, MSc, MPhil, 1 person. So it's not that actually we Odia people do not have talent. Something happened in last 20, 30 years that we have consistently decreased the manpower, and then this is the situation. So the reason why we have a panel discussion is whatever we discuss, we shall send our opinion to the government, appealing them to recruit faculty. Even in Ravenshaw University, there is a problem. There are only limited people. I know how Smriti madam is working very hard, night and day. They have a lot of other works other than research, in addition to research. So, but still, though in centers where adequate faculty are there, for example, Utkal University, they have say 9 or 10 faculty members right there. Something they can easily do. I mean, where the staffing pattern is okay, they can do. One more problem is, I heard from my students that these faculty members, they are not only to teach, they are doing the job of demonstrators and laboratory assistants also, because those supporting staffs are all gone. So how can you, I mean, you have to, in a practical class, we get into a practical class, solutions are ready, everything is ready, then we can instruct the students to do their experiment. When there is nobody, how can you run a lab? So these are the kind of things, as you know, Odisha Chemical Society is just a society. We cannot, I mean, we can simply appeal or request to them that please do it. And regarding the second point, Professor Swami, you said is a very good thing regarding curriculum. We can even have a discussion or a seminar or a webinar only for curriculum. You can, if possible, kindly arrange that. And that is very much within our OCS constitution, that we give equal emphasis to teaching and research. If you are interested, kindly organize a seminar on this curriculum restructuring. We shall take it up with the government. And
Curriculum at the honors level, I think, is more or less fixed across the state. It's only the postgraduate level where we can look at and probably rationalize with the corresponding.
Yes, absolutely, at postgraduate level. And we have, I think, other panel members, and I think Professor Ajay Behra also joined. And we have Professor Behra, can you hear, listen to us? Ajay Babu, suni parchunti ki? No, he is yet to unmute. Then I think.
Yeah, so I think we will, Professor
Paritosh
and then Paritosh, I take the liberty of asking you to talk last.
Okay, sir.
Yeah, Professor Madhusmita, could you tell me?
Hello.
Yeah, maybe you can switch on your video also so that people can, at least while speaking, so that will be good. Go ahead, please. So what we will get from you is, again, some fresh pair of eyes to look at the problem, because you are still young.
Sir, is the question directed at me?
I don't know who is the panel member?
No, not a panel member. We can go to Dr. Paritosh Mandi, but she can give some opinion.
Then Paritosh. I thought she is a panel member. Sorry.
Madam, please hang on there. You may respond anytime.
Yes. So Paritosh, questions are same. Like the kind of academic system that we have, the facilities that we have, which spreads from very small places with almost no faculty or one faculty to a reasonably functioning system, like let us say some old universities and some new universities that have come up. So how do we reach out to people? How do you sensitize them? How do you get a research culture going, or trying to make it a little better?
Thank you, sir, for giving the opportunity. First of all, I think at the outset, I would like to thank my teacher, Professor Sadhar Samal, Devasis, my friend, and Professor Mahapatra, and other members of this OCS family who really worked hard to start this baby step. I would say it's a baby step towards the development of the culture of science in Odisha. I believe, sir, science, doing science is not actually one day job, it's a generation. It may take to destroy, maybe 10 years to destroy everything, but it takes a generation to actually, start something really, which can be seen by others. I think we have a problem since last 20-25 years. If I will start, discussing about my time at MPC College, Baripada, I think that time we had really stalwart. I think many teachers, many of us may know, Badi sir, I think Tapodan Panda sir, and many other teachers who were really stalwart, and they inspire the students to do good chemistry. And I think they are the they have put the foundation for me, at least that I can tell by my experience, to really pursue chemistry as actually career. So now I think Sastra sir has already told one of the major problem of the state is we do not have adequate number of faculties. Like we had, I think, 24 faculty members during our time of MSc in Dhenkanal College. Now I don't know how many faculty members are there. So it's actually the number has gone down like anything. This is the first thing. And probably OCS cannot or may not do directly a lot of things, may approach the government. This is one thing. But what I would suggest, probably the small step that OCS can do to inspire the students. I'm little bit, more wanted to focus more towards students rather than the teachers already, because the teachers are already there and they are suffering like anything. I have several friends who are actually teaching in colleges. I know their situations. Even if I am offering that we have some facilities, you can use my facilities, but I know, although they are promising, yes, we can do, but they don't have enough time to start something, thinking something. Research we cannot do, overnight. Just I got 1 hour and I can do research. It's not like that. We have to have a real cool mind to start something innovative. We can mix two things, get something done that can be done in 1 hour, 2 hours, 5 hours. But in order to have some innovative ideas, one need to have a clear mind, which is not that much stressed. This is first thing. And that situation is probably not in, not in Odisha now. So what I would suggest, OCS as a society can start focusing on supporting some of the undergraduate and master students. Not a lot of money, but very small amount of money, just for the namesake. OCS can provide some sorts of little bit money, but a fellowship, sorts of fellowship, and we can think about having an MOU or some sorts of MOU with different organizations in India, where these students can be sent, let's say 10 students every year from different colleges for some sorts of internship or something like that. If we have an MOU with some institution, then I think the institution will not actually demand any money. For example, here we have a rule that every student who will be working here as in the internship has to pay 8,000 or 5,000 travel fee. So if we can waive off that fee and we give a small amount, just a travel allowance, let's say 2 and 4 ticket to students to come to Roorkee. This is just like an example I'm giving. A student would come and stay in my lab for 2 months or 1 month during the summer period. Even a teacher who is actually teaching in a colleges, and if he can spend 2 months in my lab and have a collaboration with my group or another group anywhere in India, and there will be direct, cooperation between these groups, that can actually start something from the grassroots level. This is one thing. And I think, without money, we probably cannot think to do any research. That is a hard fact that we have to believe. We have to start, I think Professor Swai has already told one thing, like, we have to at least inspire the faculty members in the college level to submit proposal. Yes, that's a very good thing, but again, it is related to the workload, the free mind that we have. So what we can think, the OCS can work as a sort of channel, a sort of, channel to bring some of these faculty members who are interested in research and connect them with others in the country. So we can think about, we can probably contact few of these faculty members in good places where they have facilities, and then connect them with the people in Odisha who are interested to work in that particular field. Now I can give an example. I think Misra sir has a fantastic facility for optical stud properties. I think he has the facility that is probably one of the best in the country. Now, how many times we are doing anything to connect one person who is sitting, let's say, in MPC college or any college in the state, and who is interested to do something in optical properties, approaching Mr. Sir, he might have an interest, he might be interested to contact, but we Odia people are little bit skeptical in starting something. We do not believe in advertisement, we do not believe in expressing our interest to get something from others. In that particular aspect, we are really backward. We don't approach even if we know somebody. That is even my problem, that is many other problem I have seen it.
Yes, I saw.
Now what OCS can do, it can start connecting few people who are interested in research. We can actually, I think all the members, it can start in the meetings, local meetings, it can start in annual meeting, and then connect them with the people who are actually having the facilities. And OCS can do that, job of linking them. So I think, as I told, this internship, linking people, and then some sorts of work, so even OCS, I believe it's a organization where donation will be tax free. Am I right, sir? Sir?
Yes.
So now we can try to think how we can actually get some fund which can be utilized for providing some sorts of internship and other things to students. We can just a travel allowance so that a student can go to IIS Bangalore and spend there for 2 months. So we can think about all such things. I think at least 3 different points I would like to focus. First, enhancing our ability to get some fund which can be helpful to actually sustain the second thing, like the apprentice or any sorts of internship. And third, inspiring the teachers to get a connection and be a bond, be a connection between the teacher in the state level in any college and the person who has the facility. So these 3 points, if we can start, probably at least something we can do. It will help 2 things. Once the students can be getting inspired, and second, the teachers can get some sorts of connection so that things can move forward. Thank you, sir. Thank you very much.
Thank you, Paritosh. So maybe shall I just summarize and then leave it?
Just a minute, sir. Is Professor Ajay Behra there still? Asutosh, I mean, Devasis, kindly have a look because he's a panel member. I think he joined briefly, I saw.
No, sir, his name is not there.
Okay. Okay. Then, with the permission of the chair, may I ask, I find Professor Anadi Charan Das listening to us.
Where is he, sir?
And right here, name 01 underscore Arun Rath. Could you?
I see. That is the one.
Arun Rath. Can you see the verses?
Yeah, Arun Rath, I can see.
I couldn't delete that name, so I just kept like that.
But we want to see you
and also hear you, sir.
Yeah, kindly comment because we yes.
I couldn't hear much of the discussion, so I cannot comment. But I have one suggestion which comes to my mind for helping the students in different places. Could Orissa Chemical Society hang on to develop extension lectures to teachers who are more experienced in teaching, and the students at different places can get benefit out of their lectures. Maybe for a teacher can be supported through Orissa Chemical Society to go to a college for 15 days or 10 days, and local hospitality can be borne by the college, and students can get benefit out of his lecture. This is the way the American Chemical Society does for extension lectures. And I think sometime back, 2 of the academy members came to our department to deliver lectures for 15 days. They were here. Maybe this is being continued.
Now it is not there, sir.
It was there. It was there. In that format, if we can help the students in teaching, help the teachers also, because there are not too many teachers in the college where they are needed. So in that way, one can help. Another, not only theoretical teaching or they can also help in experimental part also for short period, and this way one can help. That's my suggestion.
Thank you.
And maybe,
Okay.
is it ever possible, President sir?
Okay, sir. I'll respond to that. Very recently, we have a Orissa Government College Retired Teachers Association. We are all retired professors living in and around Bhubaneswar and other places, about 200 members. We made a resolution for the government, for a team to approach the government, asking that we want to teach in the postgraduate and undergraduate colleges wherever necessary, or any subject, because all the retired teachers are from all the disciplines. And for that, I was leading the team, and I went and met an officer very much in charge of this kind of thing. And we wanted to volunteer without any payment, because we are all retired, we are getting good pension, and we are getting bored in the home, and we have profound knowledge, and we want to disseminate that. The problem was, the answer was that you are dealing with a government institution. A government institution has certain rules, and you as an outsider, suppose go in there and interfere with their administration, who will be held responsible? Like you go and find problems with their teaching process, with their examination, or with their practicals, then who will be held responsible? This kind of questions came up, and they said that forget about it, because you can do it in private institution, but government institution, unless the government changes the rules, you cannot go there and teach. This is the situation. Even if I want to go and teach in Bhadrak College for 30 days without remuneration, without local hospitality, at my own cost, stay there and teach, I am not allowed, because the government, the persons who are present, the principal of that institute must allow me officially by getting government permission. Otherwise, I am persona non grata.
So if that doesn't work,
yes, sir,
then the students and the teachers, they are suffer. What Orissa Chemical Society can do about teaching? Can there be any other alternative for that?
Yes, sir. There are alternatives. The alternatives are that we have to prepare some lectures in video format, and we shall put it in our website for everyone to access.
That's good also. If
Yes.
the
We
other
don't
one
have
doesn't
to
work,
ask anybody's permission. We just
person to person, yeah.
Yes.
You see, the person to person contact is not there, then this is the other alternative.
Right, sir. Absolutely.
That is possible. If the students really want it, or the teachers want it, then they will take advantage of that.
Yes, sir.
That's the whole problem. You see, if person to person contact is much better, but it is not possible, as you said.
Sir, I would like to, sir, Professor Misra, respond to the last panelist, my dear student Professor Paritosh Mohanty. He had some very concrete suggestions regarding some students visiting their lab and getting.
So actually, I will summarize the whole thing
Yes.
as fast as possible. I know we are really, I mean, some of us must be very hungry now.
Yes.
And I also see that the number of attendees have now come down from somewhere 116 to 70s or so.
Right.
And that tells the state of the time. So quickly I'll go. Essentially, what Smriti Prabha madam did was to put the things in perspective, just showing us the realities of the day and the way our education system is right now, our research environment is right now, with regard to funding, with regard to almost anything. Dr. Sagar, from his view from outside, he was probably thinking about the quality of research, how to improve it, and the quality and quantity both, and how to make research better. That probably is applicable to only a few institutions in the state right now. We have clearly, although in a continuous way, but you can broadly divide them into two groups, where no research is possible kind of institutions, despite being a PG center sometimes, and where some research is possible. There's only two types. So with that, probably what Professor Sagar was telling about was those institutions where some research is possible. Coming to Professor Swami, he made some good comments. Probably I can expand on that. One is he was talking about clusters. It's a good idea if the clusters can be physically close to each other, where physically going from one point to another doesn't take much time, maybe within a couple of hours, within an hour or so by bus. So if that kind of clusters can be made, probably within the cluster they can have a kind of an environment where they can discuss chemistry, they can discuss a little bit of research if possible, and they can share resources if possible. If there is a UV spectrometer somewhere, probably very closely somebody else can access it from somewhere, maybe some electrochemical setup somewhere, and so on. If such clusters are possible, it is possible. There are some nodal issues. Anyway, universities are around. Let us say there's a Sambalpur University there is a Orissa University, there is a Parampur University. So there are nodal institutions with a little bit of facility. If the clusters can go around, grow around them, there is NITs are there. That is a possibility to be looked at. Coming to Paritosh, he made some very nice suggestions. Mostly about the suggestions, Paritosh, one of the basic premise in the suggestion was availability of funds with OCS. I'm not sure how much of funds OCS can spare for many of these things, whether they have enough funds. But at the same time, I don't know whether we can start an endowment or some such thing only for student mobility and teacher mobility, and ask for, I think we are already, I think donation to this endowment can be exempt from income tax and so on. So maybe there are some possibilities of generating some funds for creating intrastate mobility at least, which is the cheapest as of now. That may work. That's actually a good idea. And then dissemination of information. See, my feeling was in the type of institutions that you have where almost no research is possible, what can still be done is to enthuse the students, as Paritosh was also saying, enthuse the students as much so that, okay, if not at that point of time, they carry the flame and they try to go to a place where some research is possible, just to ignite the passion in them. Towards that, my feeling is right now, because of pandemic or so, the online platforms are so nicely used everywhere. It will continue. Pandemic will die out, but these platforms will continue. And this should provide a very nice, easy forum for discussions. Probably, Professor Samal, the other thing is we can create videos and circulate, but let us say for a particular topic, let us say OCS decides that for organometallic chemistry, we'll have a series of 5 or 6 lectures, essentially around a syllabus of a honors level or a postgraduate level. And then we just invite everybody. Will that not be a very cheap and effective alternative? Probably we can do that. That's not very expensive either. We don't have to physically go and disturb the institutions if the principal doesn't permit. It can be just an open portal. Students can come. We can just announce. We can just tell that, okay, for the next 5 days at this time, this will be the topic based on which these 5 subjects. One of us, the best in our state. We have, luckily, as of now, we have some extremely good teachers who have retired. So, I mean, if that talent pool can be harnessed right now, I think our students will be benefiting significantly, and there is probably a cheaper alternative to do that, as I can see. So that is from Professor. That was from Paritosh, and of course, Professor Samal kept on giving valuable inputs at every point of time with regard to the faculty and the non-availability of faculty and few places where research can be done. That's what I picked up. 2 types of institutes that are possible. If that can be done, that can be done, sir. So just one example, once upon a time in Chennai city itself, which they have a MSc program run by Madras University. One of the colleges, a private college, asked me to give a series of lectures focused on their MSc photochemistry. I go there and I find around 80 people. all of them are active. I said, your college have 80 people who are interested in photochemistry? Then he says, no, we have pulled it from 16 different colleges around Chennai, all have PG centers. They all have come to get this photochemistry, which is directly relevant to the syllabus. They gave me the syllabus. That means their photochemistry was covered by outsourcing the whole thing for almost free. So if some such thing can be done without physically traveling, our students will benefit. So I think I stopped there. I think I covered more of the other important properties. There may be some few things I missed, but if I start thinking, I will waste time. So I hand over now.
Yeah, I think I think Professor Mishra summarized everything so nicely. No more words to add. But if anything is left out, we shall have the same panel discussion tomorrow. And at the end of this, and Professor,
Is it same members or maybe different members will be better?
The same members, there will be additional input from others, if anything. We shall continue this discussion, and maybe some new points we shall add, and finally we shall draft a resolution, kind of summary of everything in written, which will be property of OCS for a discussion in our executive committee meeting. What we can do, what we cannot do, because once the finance is involved, it is bound by laws of the society. So if they do not approve, then accordingly we shall act. So we shall draft a resolution as a recommendation of the panel, and that resolution will be put up before the executive committee for a discussion. We shall tomorrow continue with this discussion, sir. Again, you have to be there and continue with this discussion. Now, I think Devasis, you can carry forward and thank the panel and the chairpersons and all the speakers present.
Thank you, Professor Mishra, for nice analysis of the facts, and all the panelists, Professor Paltosh Manti, Professor Sagar Delkar, Professor Smruti Prabha Das, Professor Sarath Kumar Swami, all have given very good points which may be very beneficial to the students of Odisha. And also I am very much thankful to our teacher Annadi Das sir for giving his kind views. Thank you all. We will again meet exactly at 10:30 tomorrow with
10 o'clock. Window will be open at 10.
The window will be open at 10, and I request all of you to join 10-15 minutes before.
What time is the panel discussion?
Yeah, the panel discussion is at 1:05.
Okay.
1:05. Yes.
Thank you, everybody.
Thank you, sir.
And officially it is over for today.
Yes, sir.
And maybe I request, where is Professor Swami? Professor Swami, Professor
Yes, sir.
Paritosh, and others, please write a few lines about your suggestion in black and white and send it